Yeah, you can start.
Okay, sir. Good afternoon, everyone. It is with great pleasure that I welcome you all for today's webinar on earthquake-resistant design of high-rise structures, modeling, analysis, and design. My name is Viha Kaur, and I will be your host for this event. We are honored to have with us today an esteemed expert in this field, Professor Dr. Yogendra Singh from IIT Roorkee. Professor Singh is distinguished scholar with knowledge and experience in the structural engineering domain, particularly in the area of earthquake-resistant design. His extensive research and numerous contribution to the field make him an ideal speaker for today's topic. Before begin, I request all the participants to please put your questions in Q&A box, and we will have a Q&A session at the end of the presentation. This webinar is being recorded, and the recording will be shared with you after the webinar. Without further ado, let us extend a warm virtual welcome to Professor Dr. Yogendra Singh. I once again thank you all for joining us, and we hope you will find this session informative and engaging. Now I quickly introduce our webinar convener, Engineer Jayant Kulkarni, who is founder member and managing director at Epicons Consultants since inception 1985. He is graduated from VZTI Mumbai. Further, he pursued masters in structures in the same college. He has specific interest in the various areas of engineering like Codal provisions, seismic retrofitting, tall buildings, concrete mix design, advanced entity and evaluation, conservation of heritage structures, and Indian aesthetics. Company has successfully completed more than 8,500 projects under his technical and administrative leadership in multiple avenues of civil engineering like structural design, project management consultancy, architecture, NDT, and infra. Now I request Jayant sir to introduce EFC.
Good afternoon, everybody. I once again welcome you at this webinar 143. I welcome you on behalf of Epicon Friends of Concrete, which is knowledge sharing platform since 1999. It is conducted under umbrella of Epicons Consultant Private Limited, which is a company ISO 9001-2015 registered. While deciding our quality policy, objective, mission, and vision, we decided one of the objectives as imparting technical knowledge to society and interested parties at large. Next. Our inspiration goes back to our friend, philosopher, and guru, late engineer A.P. Remedios. He conducted many workshops at that time, single-handedly, 6 days continuously on concrete technology. These are the few photographs of physical workshop then, which were conducting at various venues. EFC is an humble effort to create knowledge sharing platform and develop facility for continued education for practicing structural engineers, corporate consultant, government, semi-government authorities, architects, builders, and of course, faculty and students of various colleges. Let us quickly have a look at our thought leaders. It starts from Dr. V.N. Gupchup. He was principal and pro vice chancellor then. Then very loved teacher, Professor Sundaram, who was a HOD at VZTI. Next is Professor M.G. Kargil. He not only was my teacher, but also colleague, and he had been instrumental in organizing many webinars and workshops. He not only takes direct participation, but also supports financially. Dr. Sudhir Jain and Dr. Murthy is a pair who invoked the interest in all of us about earthquake engineering. And I must mention Dr. P.C. Basu. He delivered the first lecture for us at Visitia just before earthquake at Bhuj. Next. And today we are at webinar 143, webinar series we started from 101 after Corona period. So we are at 143 earthquake resistant design of high-rise building, modeling, analysis, and detailing, with specific reference to vertical irregularities in building. And we are proposing discussion on the revised draft code 13920 on 20th July 2024. And this is mainly with the appeal from IS Code Committee to send all our comment by 3rd of August. Next. With this, I thank you all. It is not only, next slide we have, it is not only me, it is my entire team. Go back, sorry, entire team, myself, Anand Kulkarni, Ravindra Deshpande, Arvind Parulekar, Parashar Mukhe, and P.P. Pandey. They are not only directors or unit heads, but they are always actively participating in workshops and webinars. Next. With this, I thank you all. So it is not only team of 6 of us, but entire staff joins whenever we conduct a physical workshop, because we require a lot of manpower, and you can see there are good efforts, especially to follow and give the messages to participants. Thank you very much.
Thank you, Jayant sir. Now I quickly introduce our moderator, Engineer Anand Kulkarni. He is Director of Epicons Consultants Private Limited. He is B Civil in 1987. Further, he studied for post-graduation with specialization in structure at SPC Andheri. He has 37 years of vast experience in the field of structural design of various types of structures, residential, commercial, industrial, malls, multiplexes, etc. His expertise includes design of tall building. He is involved in design of more than 75 numbers of tall structures ranging from 100 meter to 250 meter height for leading developers. He is a member of American Concrete Institutes. These are the glimpses of his projects: Runwal Pinnacle, Mumbai; Mahindra Roots, Mumbai; Raymond Towers, Thane. Our second moderator, Engineer Arvind Parulekar. He is BE Civil from SPC, Mumbai University in 1987. Further, he pursued Masters from MS University, Vadodara in 1990. He is working with Epicons Consultants since 1989. He is Director at Epicons Consultant, handling NDT and Structural Assessment Department. He has conducted training programs on NDT for PWD Meta Nasik, ISSE Mumbai, PWD Mumbai and Thane, Sidco Navi Mumbai, and of course, many webinars of EFC. He was appointed auditor by RMCMA for RMC 2010 and 12. He worked on more than 2,500 projects, including structural assessment project, large volume entity project, complex challenging structural design projects, and infra project. Recently, he has completed the large industrial complex assessment at Philippines. He has developed in-house well-equipped NABL accredited lab with teams of 35 engineers and technicians. Now I request Parulekar sir to give preamble.
Good afternoon, friends. Welcome to webinar 143, Earthquake Resistant Designs of High-Rise Structures, Modeling, Analysis and Design by Professor Dr. Yogendra Singh, in which he will also have special emphasis on buildings with vertical irregularities. Those of you who have attended Professor Yogendra Singh's earlier webinars on the same or similar topics do not need any background of the topic. They already know that learning of these fundamental as well as finer aspects of earthquake resistant design through first principles in his unique style gives us newer insights for dealing with high-rise structures in our practice. Rather, that's why they are here again. For those of you joining for the first time and deal with structural design, high-rise or otherwise, let me assure you that these few hours are going to make major value addition in your understanding of earthquake engineering, analysis, and designs. Unfortunately, we are increasingly becoming slaves of very powerful softwares like ETABS and think that analysis and design is actually done by ETABS and not by us. So we don't require to learn anything. Learning the fundamentals as well as finer aspects today, we will make you understand that knowing ETABS is important, but certainly not enough. We will also be expecting some insights from Professor Singh today about how to deal with vertically irregular structures, which is increasingly becoming a nightmare for professionals, especially for metropolis like Mumbai. Due to lack of horizontal space for separate buildings, we are forced to vertically combine various conflicting functional requirements like parking, commercial spaces, and even open halls with a tower of residential apartment above. Knowing fully that this is not a compliant requirement for good earthquake resistance, we don't have any option but to design these buildings. Need to understand from him how to mitigate the risks involved in such situation. So friends, without taking any more time further, I would like to give you the formal introduction of Professor Yogendra Singh. Dr. Yogendra Singh is currently Railway Bridge Chair Professor of Earthquake Engineering in IIT Roorkee. B in Civil Engineering from Roorkee 1989 and MTech and PhD in Structural Engineering from IIT Delhi in 1990 and 1994. His research interests include performance-based designs of buildings and bridges, inelastic seismic response of structures, seismic evaluation and retrofitting of structures, soil structure interaction. About 30 years of research and teaching experience and guided 18 numbers of PhD students. Published 85 research articles in various journals and presented more than 90 papers in national and international conferences. He is a member of several expert teams for post-earthquake damage surveys, convener of the BIS expert group on performance-based seismic designs of structures. Collaborated with various universities around the world with NORSAR, Norway, NGI, Norway, NTU, Singapore, Stanford University, USA, University of Edinburgh, UK, and University of Windsor, Canada, University of California, US, and University of Porto, Portugal. So I once again welcome Dr. Yogendra Singh and request him to start his sessions. Thank you.
Thank you, Parulekar Saab, for this nice introduction. I hope I'm audible, and I welcome all this evening, whosoever has joined. So let me share my screen. I hope you can see my screen now.
Yeah.
Yeah, so it should be clear now. Okay, so as Mr. Parulekar has introduced, today we will talk about earthquake resistant design of tall buildings, and focus will be on irregularities. So the common irregularities, mostly the vertical irregularities, and also some of the common irregularities which we are struggling with most of the time in actual design. Like our code defines an irregularity in terms of mode shifts, where we have to satisfy some criteria regarding the periods. We will also talk about that. And I will also talk about torsional irregularity a little bit, and floating columns, which is considered to be a big problem. In many cases, we have to provide floating columns or floating walls. And what should we do in such cases? And also the infills, the masonry infills, those are always present in our buildings in India. And we are always worried about whether those are causing any stiffness or strength irregularity. So before starting, I want to talk a little about principles of lateral load resistance. So buildings are subjected to vertical load, dead load and live load, and lateral load, that is wind load and earthquake load. So vertical load we encounter during our day-to-day life, and we understand the behavior of the buildings mostly under vertical load.
Can you come little nearer because the voice is rather low.
Okay, okay. So is it better now?
Yeah, it is better.
Okay. So we will also talk a little bit about the principle of lateral load resistance and how different lateral load resisting systems have evolved. And our code 16700, the tall building code, also has a limitation on different structural systems. So I also want to discuss the basis, how that and why that limitation has come in the code. So different lateral load resisting systems which have evolved over the years, those can be classified in these categories. So we have frames, most commonly used. So moment resisting frames. In case of steel structures, we can have moment resisting frames as well as braced frames, which we can also call frame truss. Then in case of RCC structures, we have shear walls, and then combination of shear wall with frame and coupled shear wall. So coupled shear wall is also actually a combination of frame action and shear wall action. I will explain a little. Then we have core and outrigger system, which increases the efficiency of the structural system further. And if we have to go really tall, 60 stories plus, then we have to go for either a frame truss, outrigger system, or a frame tube. So a tube which is made of frames, which combines the properties of frame and a tube. And then a tube in tube, which is similar to a shear wall core and perimeter frames. So if the perimeter frames are in the form of a frame tube, then we can call it tube in tube. And similar to that, we have end channel frame tube, where the frames are arranged in the form of a C-shaped channel at the ends. Then we have a combination of this frame tube and truss and multi-set tube. So if we want to go really tall, something like 100 story, then we have to go for this truss tube or multi-set tube. So how these systems have evolved, we can understand with this simple frame action. So what I'm showing here is a pin jointed frame. So in case of a steel structures, we can have the connections between beams and columns, either simple connections or moment connections. So suppose I have a simple connection where shear force between the or the shear force from the beam can be transferred to the columns, but the bending moment in the columns cannot be, bending moment from the beam cannot be transferred to the columns, and this can be represented by a pin here or a hinge here. In this case, when it is subjected to lateral load, the lateral load is registered by the columns as cantilever, and the bending moment at the base out of this total load P, if both columns are identical, half of the load will be transferred to both the columns P by 2 and multiplied by the height, that becomes PH by 2. So both the columns will have PH by 2 moment. But if this is the beam is connected to the column and beam is infinitely rigid, a hypothetical case where we are assuming that the beam is very, very rigid. In that case, the columns will deform in double curvature, and moment will develop at the top as well as bottom. And this moment will be PH by 4, because we can see that because of the double curvature, the effective height will be H by 2. So the moment will be half what we were getting in case of a cantilever column. So we can see here the bending moment in the columns has been reduced to half. Connection between the beam and column here, and by making the beam infinitely rigid. But in real practice, we can't have the beam infinitely rigid. So the beam is also deforming, and due to this deformation of the beam, the bending moment in column is not PH by 4, it is more than that. It is somewhere two cases. So real frames with real beams and columns are somewhere between these two extreme. Moment reduces, and part of the force is registered through overturning. So one of the column is subjected to compression, another column is subjected to tension, and similarly here in the real frame also there will be some reaction. That reaction will be less than PH by 2L, but still some compressive force and tensile force will develop in the columns, and as a result this system will be able to resist more force, because part of the force is being resisted through axial action. And from our day-to-day experience, we know any member is more strong, and not only strong, more stiff also, in axial action than in bending action. And as a result, the rigid jointed frame is more efficient system in terms of stiffness as well as strength. Now we can further improve the stiffness and strength of the system by providing a brace here, a diagonal member. So when we provide this diagonal member, then this behaves like a truss, and all the force is transmitted through axial forces, or I can say that most of the force is transmitted through axial forces. So even if this beam to column junction is rigid, very little moment is transferred to the beam, and from equilibrium, little moment is transferred to the column, and almost all the force is transmitted through axial action, and the performance improves further. Although the strength and stiffness of the bridge frame increases, its ductility is reduced. So we have to understand that the members, whether RCC or steel, those are much more ductile in bending, but those are not ductile in axial action. That happens in case of steel also, and that happens in case of RCC also. In steel, the problem is buckling, because when this member yields in compression, and we have to understand that earthquake force is much larger than the capacity, whatever structure we are designing, the earthquake force it will attract will be much more than its capacity, and as a result it has to yield. And when this brace yields in compression, it buckles. And as a result, if we compare the load displacement curve of these two systems, one is the rigid jointed moment frame, another one is this brace frame. So in moment frame, we can see that the strength, stiffness as well as ductility we get. Whereas in case of a brace frame, especially in compression, when the buckling starts, just at the yielding, the buckling starts. Even if we have designed this frame with the LYR ratio, this brace member with the LYR ratio within the limits, so slenderness is controlled, even then when it will yield, its effective modulus of elasticity, the tangent modulus, will be 0, and because of that it will buckle. Its buckling load will drop, and as a result you can see that just at the yielding it will suddenly lose its strength, and as a result its ductility will reduce. So to combine the ductility and stiffness of the brace frame with the moment resisting frame, we have eccentrically braced frames where we combine the two. So that can be done in case of steel structures. In case of RCC structures, if I have to enhance the capacity of a frame, I can do that by replacing the columns with wall. So what we are doing with the same material, same amount of concrete which I was putting in these columns, which may be square or rectangle, I put in an elongated shape. So shear wall, which has much longer length, one dimension of the cross section is much larger than the thickness. So its moment of inertia about the vertical axis here is much larger than the combined moment of inertia of these two columns. So even though this is having a frame action by rigid connection between beams and columns, integral connection between RCC beam and columns, even then the lateral resistance of this wall is much larger than this frame, because the moment of inertia, larger moment of inertia I can achieve because of this elongated shape. So this we use in enhancing the lateral load resistance of our buildings. And if we have to go 10-story plus, then invariably we have to use shear walls, especially to control that interstory drift, because shear walls provide not only strength, it provides enhanced stiffness also. Now, when we are using frames and shear walls together, we have to be careful. There is a difference in the deformed shape of the frame and the shear wall. The frame deforms like what we call a shear beam. So actually this deformed shape is that of a shear beam. And because of the lateral load, the shear force goes on increasing. The story shear in the top story is the lowest, and as we go down towards the base shear is maximum, and as a result the slope at the bottom is maximum, and as we go up the slope goes on decreasing, and in the top story it becomes almost zero. On the other hand, in case of a shear wall, it behaves like a cantilever beam, flexural action. So the moment at the base is maximum, but the slope is zero because of the boundary condition. So we get the maximum curvature, zero slope, and that curvature goes on accumulating along the height. So if we integrate that curvature, putting the boundary conditions of slope equal to zero, so we can see that the slope at the base will be zero, but the slope goes on increasing along the top. So in case of shear wall, the maximum slope will occur at the top, whereas in case of a frame, the interstory drift will be minimum at the top. And when we combine these two, so we can see that there is a push and pull between these two systems. In the bottom portion, the shear wall is supporting the frame, and in the top portion, the frame is supporting the shear wall. And due to that, there is a complex interaction. There is a change in the forces, which is known as frame shear wall interaction. When we are modeling properly these frames and shear walls interconnected through diaphragm, then this interaction will automatically take place. So it's not that we have to do anything special in our modeling. It will be automatically done, but we should be aware of this fact that we are expecting the forces in the frame to increase in the top portion because of this frame shear wall interaction. So in the bottom portion, the shear wall will relieve the frame, so the forces are going to reduce, but in the top portion, the shear wall is going to load the frame further, and the forces in the frame members are going to increase. Another combination of frame and shear wall we see in case of coupled shear. So coupled shear wall is another efficient system. Now, before starting with coupled shear wall, let me explain one more thing about frame and shear wall. So in case of frame, when it is subjected to forces higher than its capacity during earthquake, the yielding will occur. And we design the frame in such a way that the yielding occurs in the beams. And ideally, all the beams should yield or should develop plastic hinges at both ends before the plastic hinges are formed at the base in the columns. That is the ideal condition. Difficult to meet, but we try to do that by using a strong column weak beam design, and our code requires a strong column weak beam ratio of 1.4. So the strength of the column has to be 1.4 times of the strength of the beams connected to it, and that to a large extent ensures that large number of hinges form in the beams. And as the large number of hinges are forming in the beams, we have significant energy dissipation. Whereas in case of a shear wall, only one hinge will form at the base. So it is like a cantilever, where the maximum bending moment is going to occur at the base. And the shear walls are designed and detailed in such a way that the shear hinge, the plastic hinge occurs at the base. And whatever energy dissipation has to take place, that takes place at that hinge. And as a result, it is assumed, it is considered that shear wall will be able to dissipate lesser amount of energy, and that's why a smaller response reduction factor is given in our code IS 1893, where a smaller response reduction factor is permitted in case of shear wall alone buildings as compared to the frame buildings and the buildings with frame and shear wall interaction. Because when we have buildings with frame, coupled frame and shear wall system, then the hinges will form in the beams also, and larger amount of energy will be dissipated. This enhanced energy dissipation can also be achieved in the shear walls when we provide shear walls as coupled shear walls. When we couple the shear walls through these beams, then the behavior is a combination of that of a frame and shear wall. So we can model this shear wall, or we can consider this shear wall as consisting of two shear walls, which we can represent by two cantilevers, and those are interconnected by these horizontal beams. Now we have to pay attention to this junction of the beams and the shear wall. So this junction acts as rigid. So this rectangular portion which I have shown here, this will act as rigid. And when it is subjected to lateral load, when it is deforming, this rectangular section which is rigid remains straight and perpendicular to the neutral axis of the shear wall. So if this is the deformed shape of the shear wall, the deformed shape of this rigid portion will be here. Similarly, on the other side, it is going to rotate like this. And as a result, the beam in between these two shear walls, that will be subjected to very large deformations in fracture as well as in shear. And that's why this coupling beam, which is coupling the two shear walls, that is first to get damaged. So plastic hinges form at both the ends, and those plastic hinges can also form in shear. And we know in case of RCC members, shear is not, or shear yielding is not a good energy dissipation mode. So we want these to, or any RCC member to yield in flexure as far as possible. But in case of coupling beams, if we make these beams too slender, then we will not get advantage of stiffness of these two shear walls. And if we make these deeper, as generally we do, these are the deep beams, in that case, these will act as short beams and the failure will occur in shear. So we have to be careful that these beams are to be designed for very high shear, and that's why the code has the requirement of providing diagonal reinforcement in the shear walls. So how the shear wall works? The shear wall we can think as two shear walls. So these two shear walls, if these are fully separated, the beams between them are either absent or very slender. In that case, these will act as independent, and the total moment of inertia will be sum of the moment of inertia of these two shear walls. So this will be 2 into TB cubed by 12, where T is the thickness and B is this length. So this will be 2 times the moment of inertia of individual walls, that is 1 by 6 TB cubed by 12. Now imagine I join these two shear walls together. Somehow I weld them together at this junction. Then what will happen? This will act as one shear wall, and the moment of inertia will be T into cube of 2B divided by 12. So that will become 4 by 6 TB cubed by 12, or in the other words, the moment of inertia or stiffness or strength of these shear walls is going to increase 4 times. Now, this type of connection is not possible, because in that case, it will become one shear wall, and generally we need openings in between. So what we do, we join these shear walls with these coupling beams. And when we join these with these coupling beams, the behavior is somewhere between these two extremes. One extreme is when these two are fully separated, and the other extreme is where these are connected together as one integral wall. This is somewhere in between, and how much interaction will take place between these two shear walls, that will depend upon the stiffness of these beams. If these beams are stiff and strong, there will be larger stiffness and strength of these shear walls, which will be more than that of two shear walls put separately. And we can see that moment of inertia will be somewhere in between these two. And accordingly, the stiffness and strength will also be in between. So this is another very important system which we are using, and most of our buildings in the mid-height range, 20 to 40 story buildings, mostly we are having this type of system. Now, the performance can be further improved if we can transfer some bending action of the shear wall to the axial action of the column. And that we can do with what we call core and outrigger system. So suppose I have a shear wall core at the center, and along the perimeter I have columns. And if it is connected through slab, then the slab is going to deform like this. Even if it is connected through slender beams, then those beams will also be deforming like this. And as a result, some axial force will develop in the columns, but that axial force will be limited. If somehow I connect these shear walls to the columns through a rigid member at the top, then when the shear wall is going to bend, and the section which is perpendicular to its bending axis, that will rotate, it will try to compress the columns on one side, and it will try to extend. It will try to put the column on the other side in tension. And as a result, some overturning moment, which was registered earlier by the shear wall alone, that will also be registered by these columns through axial action. And as we convert binding action to axial action, we discussed that it makes the system more efficient. So we will be able to achieve higher strength and stiffness if we use this action. But we have to keep in mind that when we are subjecting the columns to high axial force, we are compromising their ductility. So their energy dissipation capacity is compromised. So we have to ensure that the column should be strong enough, column should not fail, and the energy dissipation should take place through beams and shear wall at the base. Now, different types of these core and outrigger systems are possible, and some people have also used energy dissipation devices between this core and outrigger, because this core will be subjected to large bending, especially at the top. The rotation will be maximum, and due to that, there will be large relative displacement between the shear wall core and these perimeter columns. And if we can put any energy dissipation device there, we can dissipate a lot of energy through this supplemental device. So this type of arrangement is also proposed. So this is the most desirable location where we can put dampers for dissipating energy in case of a tall building. Now, another principle which we use in enhancing lateral load resistance of our buildings is moving from solid section to a hollow section. So suppose this is a cantilever beam. In one case, it is having a solid section and it is subjected to vertical load here in this direction. So if I plot the distribution of the stresses here, we know bending stresses are tensile at the top and compressive at the bottom, and those are increasing, varying linearly till the material has not yielded. And in the linear range, this is going to be the distribution of the stresses. I can enhance the moment of inertia of this cantilever beam significantly by making a hollow section made of the same material. So the total amount of material or the area of the cross section remains same. Only thing is that I have arranged that material in the form of a hollow tube. And when I remove the material from the center and put it along the perimeter, its lateral load resistance increases significantly because the moment of inertia about this axis increases. But along with this increase in the moment of inertia, there is also a problem because of the thin sections. Now, it is not a solid section, it is a tube where the valves and flanges are thin. There is a phenomena of shear lag, and due to that, this stress distribution, which was earlier linear, it is no more linear. Rather, the stress near the corners is higher and it diminishes rapidly as we go towards the center. So earlier it was varying linearly, now it is varying parabolically, and it reduces much faster. Similarly, on the compression and tension phase, the stress was constant. The bottom fiber or bottom phase was having same stress throughout. Here it will not remain same throughout, again because of the phenomena of the shear lag, because of the thin section here. So maximum stress will occur near the corners, and as we go towards the center, this stress is going to reduce. So we can enhance the capacity of a solid section by putting it in the form of putting the material in the form of a tube. Its stiffness and strength is going to be enhanced, but we have to keep in mind that this phenomena of the shear lag will take place. It will reduce its efficiency to some extent, but still it is having much more resistance than a solid section. Now, in case of tall buildings, we are providing frames, beams and columns throughout the building. So we can have a regular grid pattern, or if we remove the lateral load resisting columns from the interior near the center of this section and put those along the perimeter. So I will have closely spaced columns along the perimeter, because all the lateral load resisting columns I'm putting on the perimeter, and those will also be connected by deep spandrel beams. So deep beams, which we call as spandrels, something like coupling beams. So we can visualize it like this, that these columns are placed at a spacing of 3 meters. Size of the columns is something like 1 meter by 1 meter. Similarly, the size of the beams is also like 1 meter by 1 meter. So each panel here is 3 meter by 3 meter, and out of that 3 meter by 3 meter, 1 meter at top, 1 meter at the bottom, and 1 meter from the side is, or rather half, if we consider the beam contributing to the top story and the bottom story both. So half meter from the top, half meter from the bottom, that will be covered. So we can think this is like a tube where we have punctures for these windows here. So we have made openings in the tube, or we can think this as a tube made of frames. So where 4 frames are combined together in the form of a tube. And in the interior, we have only a few columns which are designed as gravity columns, which are having much smaller size, and hence those are flexible, and those are connected with long beams. So their stiffness of those as a frame is very small, and we can design those as gravity columns. So only few columns are left inside, and almost all the columns are put along the perimeter, and that makes it a very effective structural system, similar to the tube section which I discussed. But here also, if we apply the load, let us say lateral load is acting in this direction, although we know lateral load is not acting any one specific direction. But for our understanding, let's consider the case when lateral load is acting in this direction, then this frame will act like a flange, whereas this frame will act like a valve, and opposite frames will also act like flange and valve. So this flange will be in compression, this flange will be in tension, and similarly these two valves will be subjected to bending. And the stress distribution here due to shear lag, that will also not be uniform, or the column forces which we are going to get, those column forces will also vary in this fashion. So if it was having an ideal bending behavior, then the column forces in the flange should have been uniform. But those forces are not uniform. We will get higher forces near the corners and smaller forces near the center of the flange. Similarly, in the web, this distribution of the column forces is not going to be linear. It will be parabolic, it will be curvilinear. It will drop towards the center much faster than what will happen in the ideal case as a linear variation. So this shear lag phenomena reduces the efficiency of this frame tube system to some extent, but still it is a very effective system in RCC as well as steel buildings, and many of past buildings have been constructed using this phenomena. Now we have to keep in mind, when you look at the structural systems of tall buildings which have been constructed in the world, then we see different structural systems have been used. So it is not that any particular system has been used for all the buildings. So this frame tube, it has been used in many buildings, but not in all. Other buildings have been also constructed with other structural systems, and we will talk about that also. So what we see here, these are the World Trade Center Twin Towers, which were destroyed in the terrorist attack. All of us know. So this was a steel tube. Once upon a time, this was the tallest structure, the tallest building, and this is made of steel tube. So you can see that closely spaced vertical columns, and those columns were connected by deep beams. In the bottom, because of the architectural regions, the spacing between the columns was increased, and columns were made much stronger, and a transfer girder was provided at that level. We will talk about the design of the transfer girder later. Now another system which is an improvement above the frame tube, where we provide a shear wall core. In case of a tall building, there will be a large service core. So that service core will have all the services staircase and escalators or elevators, sorry, not escalators, but elevators and lifts. So we can have a large inner core which will house all these services, and that can be constructed with the shear wall, because such ventilation may not be needed as we need in the rest of the building. So outer tube may be made of frame tube, the inner tube may be made of a shear wall. So this system we call a tube in tube system, and this will have a behavior something similar to frame and shear wall. So it is also a coupled system, and similar behavior, similar type of interaction between the inner core and the outer core we expect here. But a combination of the two makes this much more stiffer, and we can go for larger heights. Then we can combine the bracing system with the frame tube. So left hand side shows a system for steel structures, steel buildings, where a mega truss, so which is crossing several stories. So a mega brace or mega truss along with the frame tube is provided. So we know that this diagonal members, the braces, these will enhance the strength and stiffness further, and as a result, the larger height can be covered. Now we have to understand that when we are providing these diagonal members, the ductility is compromised. Ductility will be reduced. So this choice has to be made depending upon the location. So in case of tall buildings, we know that the wind starts governing, and in case of very tall building, 100-story or so, wind load will be governing. And if the wind load is sufficiently higher than the earthquake force, then we can design our structure to remain even elastic during earthquake. In that case, the energy dissipation is not needed, and there we can go for this system, especially when we are having low seismic zones, like coastal areas where the wind forces are much larger and earthquake forces are not that large. Now, similar arrangement, although not very popular, can be made in case of RCC buildings also, where these panels are filled with concrete in such a way that these also act like a brace, a truss member in case of a steel structure. So it can enhance the strength and stiffness of a tall building. And those who are designing tall buildings, they understand that in case of tall buildings, it is the interstory drift which is governing the design. It is not the strength which is governing the design. So enhancing stiffness becomes a key objective. And these types of braces or arrangement of panels can enhance the stiffness and reduce the interstory drift significantly. Now, to take care of or to minimize the effect of shear lag, another system which is called as bundled tube or multi-cell tube is developed, where multiple tubes are bundled together. Or we can think that this is a frame tube having multiple bags. So several bags are there. And due to that, at the intersection of the bab and the frame here, along these columns, the forces will be increased almost to the same level as the corner columns. So here also the forces will increase, and the shear lag will take place between these two columns. And due to that, the efficiency of the system will increase. So these different types of systems can be summarized like this. And this figure shows the tentative height. Now, as I said earlier, there is no rigid rule about the height, that which system can go up to what height, but the height range in which different structural systems are economical, that is given in the textbook. So in the tall building textbooks, so I think I have taken this from B.S. Taranath's or maybe Fintel's handbook, I do not remember. So one of these two books I have taken. So we can see that up to 10-15 stories, we can have a semi-rigid frame. Then for taller buildings, we can go for rigid frame. Then we can go for braced frame. And you can see here, these are not concentrically braced frame. These are eccentrically braced frame because concentrically braced frame lack ductility. So eccentrically braced frame are preferred. And this is the core and outrigger. So core is also made of braced frame, eccentrically braced frame, and these outriggers are also made of eccentrically braced frame. And this is the tube, and in the tube you can see that inside there are only few columns which are resisting only gravity load, and all the lateral load resisting columns are put on the perimeter. In between the frame, braced frame, and the frame tube, other systems are also possible where we can arrange the lateral load resisting columns along the perimeter, but not as a closed tube, but in C shape. So the advantage of this is that you can have larger wave widths for ventilation as compared to a tube. The tube will be just like a tube with openings, small openings. Here we can have larger openings. And we can have a C section and I section like the one shown here. So we can see that the efficiency goes on increasing gradually. So the efficiency increases from here to the frame tube, and then we have this multi-cell tube and the truss tube. So truss tube is considered to be the most efficient system where we can go to much taller height. Now, similarly, in case of RCC buildings, we have rigid jointed frame. So we can go theoretically up to 20 story, but usually up to 10 stories. Beyond 10 story, it becomes difficult to satisfy the interstory drift. But theoretically, it is possible to go as taller as we want. So then we have the frame and shear wall, and we have the shear wall system where we are using shear walls alone. Then we have frame and shear wall. So we can see that the frame shear wall, the dual system, is more efficient than shear wall system. And up to 50 story, it is suggested in that particular reference. Then we have frame tube and tube in tube, where inner tube is made of shear wall core, and we have modular tube or multi-cell tube or tube in tube, bundle tube system where we can go even taller. So these are the structural systems in case of RCC buildings, and we can see that the efficiency is increasing, and accordingly we can go taller in those. But these limits are only tentative, which is defining that which system is more efficient. But it is not that if you want to have a system which is, let's say, not that efficient, it may be not economical, but there is no limit that these buildings, so these heights are not to be treated as limits. But in our code, we all know IS 16700, there are rigid limits. So well-distributed structure, before that moment frame. So in zone 4 and 5, moment frames are not allowed for buildings which come in the category of tall buildings, that is up to 50 meters. So naturally, those are more than 10-story buildings. So moment frames are usually economical in the range up to 10 stories. Beyond that, the problem occurs with the interstory drift ratio, and those become uneconomical. So that's why in zone 4 and 5, in tall buildings, frames are not allowed. But in zone 2 and 3, where the earthquake forces are smaller, these are allowed, and up to 80 story is allowed in frames alone. 80 meters, not 80 stories, 80 meters. It is allowed. The building is allowed to have frames alone. Then when we have well-distributed structure walls, so we know this is more efficient system. So in zone 5, we can go up to 120 meters. If we have a structure wall plus moment frame, we can go higher. And same is applicable to structure wall plus perimeter frame. So structure wall plus moment frame and structure wall plus perimeter frame, it is the similar limits are given in our code. But when we have frame tube, and that frame tube may be having an inner tube. So here structural wall, the structural wall can be in the form of inner tube, which is more desirable, more common from the functional regions. Otherwise, it can be a distributed shear wall also along with the frame tube. Then the code allows up to the maximum stories, the maximum height, 180 meters in zone 5 and up to 250 meters in zone 2. Now, although we know that Theoretically, there is no limit. You can go for any height in any structure system as long as you are able to satisfy the Codal limits. But IS 16700 provides these guidelines, and usually in practice we are following this. But theoretically, these limits are not sacrosanct. These are just based on the judgment of the code committee. The code committee has identified there is no theoretical reason that why can't we go more than 150 meters in case of structure wall and moment frames. We can go if we can justify the design that it is having adequate strength, stiffness, and ductility. So slenderness ratio is also governed. Actually, slenderness ratio is governed by the overall stability of the structural system. So if we are having a very slender building, then the windward side is going to develop large tension, and that tension can be more than the gravity load which is attracted by those columns, and as a result the columns can go into tension, or those can have very little axial force remaining. So that's why the slenderness ratio is specified. But if we can provide proper design of the foundation, and we can check that our columns are still having ductility, significant ductility, or the desirable amount of ductility, we can go beyond this also, and such buildings we can call as code exceeding buildings, and we can justify their design using appropriate design methods. I can say that as the performance based design or nonlinear analysis. So based on nonlinear analysis, if we can justify, we can show that the performance of the building is okay, we can go beyond that also. Now the most common type of system which we have, somehow this black strip is coming in my screen. Is it coming in your screen also, or you are seeing it clearly?
No, we are seeing it clearly.
Okay. So if you are seeing it clearly, then it is fine. So
Yeah.
on my screen, this heading is not visible. So some command tab is coming. Anyway, so our common tall buildings which we are constructing these days are having a tower and then a basement and sometimes a podium above the basement also. So this podium, which is a larger size structure at the base, and if there is a basement, then we will be having retaining walls. That makes it very rigid, and it has the so-called backstay factor, and this causes the most common type of irregularity in our buildings, where the bottom is very stiff. Although it is not considered, it is not defined as irregularity, but it poses some challenges in analysis and design. So there can be a basement and there can be multiple towers, single tower or multiple towers, and the stiffness of the tower and the basement is very different. And when we perform the modal analysis or free vibration analysis, the initial modes do not have any mass participation from the basement. As a result, you will not get 65% mass participation. Mass participation will be much less. And if you really want to have 65% or 90% mass participation, then you have to consider a large number of modes, more than 200 or something like that, depending on what is the difference in the stiffness of the two systems. So you have to consider a large number of modes. Alternatively, okay, so the actual problem is something like this. We have the soil and we have the building, and that building is embedded into the soil, and the soil which is in the vicinity of that building, that soil will be interacting with the building, and the earthquake motion will be transmitted through the soil, and due to that a complex interaction between the soil and the building takes place, which we call soil structure interaction. And if I have to simulate this complete soil structure interaction, I have to simulate the soil also. So the soil will be simulated as a continuum using solid elements, whereas the building can be simulated using a combination of skeletal elements like frame element, so beams and columns, and sometimes even shear walls, I will explain later, can be modeled using frame elements. The retaining wall, I have to model as shell element, and the soil surrounding as solid elements, and I have to apply a ground motion at the base of this model. So this model becomes very complex. It is very difficult to analyze this model, and even in research, I have not come across the time taken by the system will be very, very large. So this type of system is seldom, rarely analyzed. Although this is the most accurate simulation of the problem. So what we do, we have to take into account the load part. So when we are having a podium which is having shear wall, or we may have a basement which is having retaining walls, and these retaining walls also act as shear walls in plane direction and out of plane direction, those are subjected to earth pressure. So this bottom portion becomes very rigid, and this tower, when it is vibrating at the topmost level of this podium, those are subjected to reactions here. And as a result, a large shear force get transferred from this tower portion to the podium or the basement portion. And this top slab, which is through which the shear force transfer takes place, that we call backstay. And this phenomena we call backstay effect. And this backstay effect changes the distribution of the bending moment and the shear force within the core. So if we look at the distribution of the load, so this load, the triangular load, which is acting, let us say it is due to earthquake, increasing linearly. Actually, it increases in proportion to the mode shift, but let us assume that it is linearly increasing. And as a result, it is getting transferred into the shear wall. And at the bottom here, at the top of the podium, where we are having this backstay effect, we can see that the deformation here becomes almost zero, or it reduces significantly. So what we see here, this is the deformed shape of the core or the tower. So the tower has the maximum deformation at the top. Near the backstay, or at the backstay, the displacement is almost zero because of the rigidity of the backstay. And then the deformed shape changes, the curvature changes. And as a result, the direction of the bending moment. So bending moment at the top is zero. It goes on increasing. At the backstay level, the maximum bending moment occurs. So maximum bending moment does not occur at the base. The maximum bending moment occurs here. That's why this backstay level is very important. And how much moment will occur here, that will depend upon how much stiffness is provided. If the basement or the podium is infinitely rigid, one extreme case, then the bending moment which will be occurring here will be close to the fixed base moment which will occur in the tower when the tower is fixed at the backstay level, at the top of the podium if it is fixed. If we look at the shear force, a change in the direction of the shear force takes place at the backstay level. So the shear force builds up, becomes maximum at the backstay level, then it changes its direction and again it reduces. So bending moment in the tower portion below the backstay reduces, whereas the maximum bending moment occurs at the backstay level. So this phenomena we have to properly simulate. Our model, whichever model we are using, should be able to simulate this phenomenon. So two approaches are used for that, depending on the stiffness of this backstay and what rotational stiffness we are getting at the base. So our structural system can be idealized like this cantilever, which is connected by a spring, and this spring is representing the stiffness of the backstay. And depending upon the size of the retaining wall, this backstay stiffness can be anywhere between 0 to very large, close to infinity. It can be there where the displacement here is 0. And the rotational stiffness will be provided by the raft foundation present at the base of the basement or the founding level. So this rotational stiffness will come from there. So depending on how much stiffness is mobilized through this backstay, the behavior of the structure will depend. And during large forces like earthquakes, the backstay slab, the top slab of the basement or the podium, that will yield locally. And due to that, its stiffness is going to change. So estimation of exact stiffness, which will be available during earthquake, is difficult. And that is why the code suggests a sensitivity analysis. So a sensitivity analysis is performed where varying stiffness of backstay are considered. So two approaches to consider this effect or modeling of tall buildings or the components of the tall buildings are there. One is the skeletal approach and another is the continuum approach. So some of the members in the structure, tall buildings, those are having distribution of mass along a line or which can be represented by a line. We call those as the skeletal elements. And examples are beam, column, braces, trusses, and in some cases shear walls. I will explain that the shear wall can also be modeled as skeletal elements using a frame element or using a line element. And we do the frame modeling using skeletal elements. On the other hand, we have different types of continuums, 2D and 3D continuums. So 2D continuums are those where the mass is distributed in two directions, in two dimensions, like the shear walls, slabs, and foundations. Those are 2D continuums. And 3D continuums are those in which the distribution of the mass is in 3D, like the soil. So soil is having distribution of mass in the 3 dimensions. So that is to be modeled using solid elements or 3D elements. And we have different types of elements available for this: plane stress. Then we have plate elements, shell elements. Most commonly, we will be using shell elements, which have the bending, out of plane bending capability of plate, as well as in plane resistance, which is coming because of the plane stress element or the so-called membrane elements. And soil is to be modeled using brick elements or solid elements, which are having 3D characteristics. So here the equivalent model of a C-shaped shear wall is shown. So we can model any shear wall, whether it is C-shape or U-shape, or it is even a closed shear wall, or it can be a planar shear wall. So a planar shear wall can be modeled by a single element, single frame element along its center. If it is a C-shaped shear wall, then it is modeled using 3 frame elements. So each element here is representing one portion of the shear wall. So this is, for example, this is web portion and these two are the flange portions. When the force is acting in this direction, then this will act as web. So web is represented by one frame member. The flanges are represented by separate members, and these members are interconnected through rigid elements. So if I connect them rigid, then I can mobilize the action due to the C-shaped shear wall. Alternatively, these shear walls can be modeled. The same shear wall has been modeled using frame elements and using finite element and shell elements. So here, all the panels of the shear wall has been modeled using shell elements, and those shell elements are interconnected at the junctions, and as a result, the overall behavior of the shear wall, where one panel is acting like a web and the other panels are acting like flanges, it can be mobilized. So we can model using shell element, we can simulate the same behavior using skeletal, the frame elements also. The advantage of frame elements is that the number of degrees of freedom is very small as compared to the number of degrees of freedom here. And we have to keep in mind, whenever we are modeling any structure or any component using continuum finite elements, adequate meshing is to be done. That means the size of these shell elements should be sufficiently small. And how much is sufficiently small? That is not known. That we can get only from a sensitivity analysis. So what we do, we perform analysis with different mesh sizes and then try to obtain the results. And we go on reducing the size of the mesh till the results are converged. When the results are not affected by the size of the meshing, or our results becomes meshing insensitive, in that case, that size of the meshing we have to use. Generally, one story of the shear wall, if we are meshing with 8 to 10 elements in both the directions, it is reasonable. And this is a common mistake what our designers do. They usually use default meshing, and default meshing may be very coarse. A shear wall element can be just divided into 1 or 2 elements. So there we are not going to get the proper distribution of the stresses, and when the bending moment and shear force we will calculate for designing of the shear wall, those will be erroneous. So we have to perform a sensitivity analysis to decide the size of the meshing, and that mesh size should be sufficiently small, or sufficient number of nodes should be available in each direction, so that the distribution of the stresses can be captured, and the bending moment and shear force which we will get by integration of these stresses, those should be reasonably accurate. Now that's why a frame modeling, where we are representing shear walls with a single column, a white column, or multiple white columns, that is more desirable. So here a frame element is shown for this shear wall core. So here we can see that the shear wall consists of 2 portions, C-shaped portions. So we have RC walls here in the form of C-shape, we have here in the form of C-shape, and then it is interconnected by coupling beams. So this we can model by frame elements, by providing one frame element here, one column here, one column in the center of this web, and another column here. So 3 columns to represent this one C-shape, and another 3 columns to this C-shape, and those are interconnected through these beams. Whereas these columns, these 3 columns, these will be interconnected by this rigid element. So this black horizontal element which I am showing, these are nothing but the rigid beams. So these columns will be interconnected by rigid beams, and in between these will be connected by actual beam, that is the coupling beams. So this thin line here, this is the actual beam, and the dimensions, it will have the dimensions of the actually provided beam. Whereas those columns will be interconnected through rigid beams. Rigid beams means that their stiffness is much higher than the normal beams. So if the stiffness of these beams is at least 100 times of these beams, so if we are providing the stiffness 100 to 1000 times, then the purpose is served. So we cannot provide a stiffness lesser than 100 times, because in that case this will not behave as rigid, and these 3 columns will not be properly integrated together. And if we provide a very high stiffness, let us say 1000 times, more than 1000 times of this actual beam, then there will be ill conditioning of the stiffness matrix, and there will be convergence problem, and we will not get accurate results. There will be numerical errors. So the stiffness of these beams which are interconnecting these 3 columns, white columns, that is very important. Now if we are modeling these shear walls using shell elements, then coupling beams we can either model again using shell elements, but we have to make a sufficiently fine mesh there, or we can model the beams as normal beams or a frame element. Now these frame elements are to be interconnected with the shell elements, and these are connected at one point, one node. And if we are connecting these at one node, then sometimes what happens, that the connection becomes flexible. So 2 approaches are suggested to take care of that, that this end of the beam is not connected to one member, one node alone. It is interconnected with nearby nodes also through rigid elements. So that provides sufficient rigidity at this connection. Or alternatively, we can provide fictitious beams here. So in the shear wall, there is no beam actually, but we can provide a fictitious beam here, which is rigid, and then our normal beams we can connect with this. And in that case, the connection between the shear wall and the real beam will be quite rigid through these fictitious rigid beams. And these rigid beams will have the same stiffness as I said earlier. So although there is no beam provided here, but just to make the connection between the beam, that beam may be a coupling beam, that beam may be the beam coming from the frame and connected to the shear wall here. So it is good to have a fictitious beam here, and that beam is rigid. In that case, the connection between the shear wall and the beam will be established as a rigid connection. So just to show you an example, this is a 20-story building. So 20-story building, which is having shear walls along the perimeter, and there are 4 columns at the center. So the lateral load is registered mostly by these frames, and very little force is registered by these columns. But just to give you an idea how the modeling can affect the results, or how much our results are sensitive to the modeling, 4 types of models are shown here. In the first case, the shear wall is also modeled using shell elements. The slabs are also modeled using shell elements, and a meshing of 10 by 4. That means the 10 nodes are considered along the length or in the horizontal direction in each shear wall, and 4 elements are considered along the story height. And the panels here, the slab panels here, those are then meshed as 4 by 4. Here, the meshing along the height is reduced to 2, and meshing in the horizontal direction is reduced to 5 elements. And here, 4 by 4 meshing is used. It is same as this model number 1. The only difference is that those fictitious elements, which I was talking in the previous slide, those fictitious beam elements were also modeled, so that a rigid connection between the beams which are connected with these columns and the shear wall can be established. And in this model, all the all the shear walls are modeled as frame elements. So these are modeled as column elements at their center, and all the slabs are modeled as rigid diaphragm. So we can see that computationally, this is a very light model. The number of degrees of freedom are very small. And here I have modeled only the tower portion, the 20-story tower portion. The basement portion is not modeled. So it is assumed to be fixed at the ground level, and then the results are compared. And if you see the results of these 4 models, first the periods. So you can see that the periods are close, but model 2 is getting larger period, slightly longer period, and all other models are having close to this model 4. So model 4 is the one in which we have modeled the shear walls also as wide columns, not using shell elements. So you can see that the period is very close, almost same, and the slabs have been modeled as rigid. So because we were having here the solid slab, there was no opening, no cutout in the slab. So we could model that as rigid diaphragm. So all the slabs have been modeled as rigid diaphragms, and the shear walls have been modeled as frame elements. So we can see that periods we are getting very close. And if you look at the base shear, that's also almost same. And mass participation ratio, all the parameters have been compared, and we can see that this model, which is very light and simple model, that gives us the same results as we are getting with finite element models, as far as the tower portion is concerned. So we have to keep in mind this is applicable for tower portion. Now we have the basement also. So when we are analyzing the building with basement, then 2 approaches are possible. In the first approach, which we also call substructure approach, in substructure approach, we are modeling the tower and the basement portion separately. So tower portion can be modeled using any of the 4 models which we discussed just now. The basement which is having retaining walls, that is to be modeled using shell elements. So the basement we are modeling using shell elements, and the portion of the tower which is going into the basement, that can be modeled in the same manner as the upper portion of the tower above the basement. In the same manner we can model it. So the tower portion is modeled separately, it is analyzed separately, and the basement is modeled and analyzed separately. Whereas in the second approach, we make a single model of the tower and basement, a coupled model. So this is also called a coupled approach. So here the tower portion again can be modeled either using white columns, frames, elements, or using shell elements. Whereas the basement portion, the outer retaining wall of the basement, that is to be modeled using shell elements. So that has been modeled using shell elements. Now the problem with this model, the coupled model, why this approach 1 is to be used. One reason is that we are modeling, we are analyzing two systems separately, so the computational time is reduced. But more than that, there is a problem in scaling of the base shear. We know a BB bar by BB correction is to be applied to this building, and the period formulae which are available in the code are for this type of building. For the building with basement and the tower, such base shear correction formula are not available. Period formula is not available. So what we have to do, we have to ensure that the base shear at the top of the basement, at the backstay level, that should be scaled with the formula given in the code. So that becomes much easier when we are using the first approach. So in the first approach, we will perform the analysis of this tower, assuming it to be fixed at the top of the basement. And the base shear scaling, BB bar by BB correction, will also be applied accordingly. And those forces which we are getting at the base of this tower, we will transfer to the tower portion in the basement. So those forces will be applied. In addition to that, the self inertia of this basement. Now here this basement we have analyzed by fixing at the base. So its period is going to, this is going to be very, very rigid, and it's difficult to perform its analysis. So what is done, we will assume that its period is in the flat range of the response spectrum. So SAYG we can consider as 2.5, and dynamic analysis becomes difficult, so we can perform the analysis statically. So static analysis we can perform, where whatever forces we were getting at the base of this tower analysis we have performed dynamically. So either using response spectrum method, mode superposition, or time history, we can perform analysis of that. But whatever reaction we are getting at the base, those reactions we will transfer here, and the self inertia of the basement portion can be considered either dynamically, performing a dynamic analysis, or statically considering SAYG equal to 2.5. So that analysis we can perform, and I will show later that this analysis is quite conservative. The problem occurs in this, we can perform an analysis in the coupled analysis using any method, either a static method, although static method is not permitted for such tall buildings. So we have to go for mode superposition, response spectrum method, or time history analysis we can perform. But when we are doing a mode superposition method, there is one problem, that it is difficult to excite the modes in which basement is participating. So getting 90% mass participation is going to be very difficult in this case, and we have to consider a large number of modes, maybe more than 200, to get 90% mass participation. So that we have to keep in mind. Second problem is how to do the base shear scaling. If I apply the same scale factor over the whole building, which I am getting at this level, it will be too conservative. So that may be too conservative for the basement portion, because basement portion is already in the peak range of the period. And if we are scaling that again with the scale factor, the base shears here may be much larger. So how to apply the base shear correction, that is a challenge in this case. Now, whatever in the first case, whatever forces were occurring at the tower base, those are to be applied with the basement that I have already explained. So if we compare the results in the two approaches, so the period, if we look at in the substructure approach and the coupled approach, in coupled approach, the basement and the tower single model has been used. So we can see that the period in the second case is longer. The first period, here we are talking about the fundamental. So in the fundamental mode, even in the coupled model, actually only the tower portion is vibrating. So tower portion only is participating in this mode. And if we compare the periods, here even the fundamental mode is longer. The reason is that in substructure approach, we have assumed the tower base to be fixed. Whereas in the real model, the tower base is not fixed. Whatever small deformation is occurring in the basement, that will be transferred to the tower base. And as a result, it is slightly flexible. So you can see that the period has slightly increased in both the directions. If you look at the story shear at the base of the tower using response spectrum, and this is before performing BB bar by BB correction. So you can see that both the methods are giving almost identical, very close base shears, whether we are using substructure approach or coupled approach. You can see in the coupled approach, the base shear is slightly larger, although the period here was smaller. This is because, period here was longer, and when the period is longer, the SA by G will reduce. But the base shear which you are getting, story shear which you are getting at the base of the tower, that is at the top of the podium, that is slightly higher. And the reason for that is in the mass participation, because the mass participation here increases. And not only the fundamental mode is participating, other modes are also participating. And due to that, the base shear or the story shear at the base of the tower actually increases. Of course, when we scale the base shear in both the cases, the base shear will become same. But when we consider the base shear at the base of the basement, then you can see that in this substructure approach, the base shear we are getting is much higher. And the reason for that is that we have considered the static analysis, static forces with SA by G considered as 2.5, because the period we have assumed to be in the range of the response spectrum, where the response spectrum is flat. So we have considered SA by G is equal to 2.5. Whereas in actual model, the period we will see later, it is much less than 0.1. And because this period is less than 0.1, so what happens? The response spectrum value, SA by G value in the response spectrum reduces from 2.5, and it is somewhere between 2.5 and 1. So due to that, the base shear which we are getting in the substructure approach is on conservative side. So this conservative, substructure approach is much simpler. It gives identical story shear in the tower portion, but it gives conservative base shear in case of the basement portion. So that we have to keep in mind. If we can design for this reasonably, we can go for this substructure approach. But in some cases, it becomes difficult to design the retaining walls, although those retaining walls are quite long in plane action, but it becomes difficult to design those. In that case, we can go for the coupled approach, and we can see that the stresses in those retaining walls, which also act as large shear walls, those stresses will reduce significantly. If we look at the bending moment in the shear wall, in the tower portion, then we can see that the coupled approach is resulting in much lesser bending moment. Although the shear, base shear is either same or higher, but the bending moment in the shear wall is reducing. That is because in case of substructure approach, the decoupled approach, we have fixed the shear wall at its base. Whereas here it is supported on the top of the basement, and that basement is providing some flexibility, and due to that the bending moment in the shear wall is reduced. So this substructure approach is conservative in all respects. Now we can also have a look at the modal characteristics. So here you can see in the initial modes, only the tower portion is participating, and that's why the mass participation is small. We get only 52% mass participation in the fundamental mode, which is quite small. And in second mode, we get similar mass participation in the other direction. So if we consider the first three modes and we look at the Codal requirement, that in the first three modes, 65% mass in each direction has to participate. So we can see that we do not get that. But here we have to keep in mind, this is not because our building is irregular. This is because the building is having basement, and a lot of mass is concentrated in the basement, and that portion is not participating in the initial mode. So basement participation comes in 42nd mode, and it is also 3.8%. In 47 mode, it is roughly 10%. So you can see at very large modes only, we get participation from very higher modes, we get this mass participation, and we can get this close to 99% participation in 300 modes. And even up to 47 modes, our total mass participation is only 88% in x direction. So even 47 modes are not adequate because our basement is participating here. And if you look at the period and these modes, you can see that the period is only 0.048, less than 0.05. So it is much less than 0.1%. And if you look at the shape of the response spectrum, it is in this range where the response spectrum, normalized response spectrum, is increasing from 1 to 2.5. So in case of decoupled approach, we have assumed the basement to be infinitely rigid, and we have assumed that the period will be in this range, and SA by G we have taken as 2.5, whereas in reality it is in this range, and that's why the second approach is giving us lesser base shear. Now, to study the effect of the size of the basement, we have performed a parametric study where 2 stories in the basement, 3 stories in the basement, 4 stories in the basement have been considered. So different number of stories in the basement and different base. The plan area of the basement has also been varied. And this analysis has been performed. And what we get here is that as we increase the size of the basement, and if we look at the period, so this T1 is corresponding to tower portion, the fixed base model, whereas B2 and B4, these are representing the 2-story and 4-story basement, and these are the number of bays. So we can see 2 bays, 3 bays, 5 bays outside the tower portion. So the size of the basement goes on increasing. And if you look at the period of vibration in different direction, so the smallest period, the shortest period we get in the fixed base condition. And as the size of the basement goes on increasing, the period elongates slightly because this basement is providing some flexibility. And larger the size of the basement, more will be the flexibility. If the basement is smaller, it is close to the tower, the flexibility provided by that will be less, and the flexibility will be provided more if the depth and plan area of the basement is increasing. So we can see that the period of vibration is increasing, and the basement is participating in these modes. So as the basement is smaller, it is rigid, its participation is smaller, and that participation also comes in a higher mode. If the basement is increased in size and depth, its participation is also increasing, and that starts occurring at a smaller number of modes. If we compare the base shear in the bottom story of the tower, we can see that the base shear is first reducing and then increasing. So this is without basement. Here we have the 2-story basement and then 4-story basement. So as the size of the basement is increasing, we can see that the story shear goes on increasing. It is interesting. The period is elongating. And when the period was elongating, you might have thought that when the period is elongating, SFIG is reducing, so base shear should reduce with the increase in the size of the basement. But actually the base shear, and here base shear we are talking about the base shear in the tower portion. That means the bottom story of the tower or the ground level story of the tower or the story just above the basement. So in that story we are comparing. So although SFIG is increasing, but as I have shown that the mass participation, the modal mass participation is increasing with the increase in the size of the basement. As a result, the base shear or the story shear in the tower is increasing. That happens in X direction, that happens in Y direction also. And this is the bending moment in the shear wall. So bending moment in the shear wall, we can see we are getting maximum bending moment in case of fixed space, because there the shear wall is assumed to be fixed. But as the size first it reduces when the basement is smaller, and as the size of the basement is increasing, we can see that the moment occurring in the shear wall goes on increasing. And but in all these cases it is close, not very large difference. So same happens in X direction, same happens in Y direction. Then backstay sensitivity, which our code is asking. So we can model the slabs of the tower portion using rigid diaphragm. If the slab is solid, we can model using rigid diaphragm. That saves a lot of number of degrees of freedom, and the size of the problem is small, computational time will be reduced. We can use that. But in the basement portion, we cannot use rigid diaphragm command. There we have to model the slabs using shell elements, and we have to use stiffness modifiers. So stiffness modifier of 0.25 is suggested in general. So if we look at our code, it suggests a stiffness modifier of 0.35 in case of beams, 0.7 in columns. So all beams and columns we have modeled using these stiffness modifiers, whereas the slabs have been modeled using a stiffness modifier of 0.25, which is general, which is given in IS 1893, and sorry, not 1893, 16700. And in case of backstay, there is an upper bound and lower bound. So that upper bound is given as 0.5 and lower bound is given as 0.15. So these stiffness modifiers also we have used. And what we see here with the upper bound modifier, the period of vibration is slightly smaller. With lower bound, it is longer. Whereas with the 0.25 stiffness modifier, it is somewhere in between. So we can see that the period of vibration itself is quite sensitive to the stiffness of this backstay. So backstay stiffness has a major role. And if you look at the story shear at the base of the tower, so we can see that also goes on increasing with as the stiffness modifier is increased. So model number 21 and 22, if you look here, model number 21 is upper bound. 15, as I have shown in the previous table, that was with 0.25, and 22 is lower bound. So this is upper bound, this is lower bound. So in case of lower bound stiffness modifier, the base shear is higher. In case of upper bound modifier, the base shear is lesser. So the base shear also gets affected. Even in the tower portion, it gets affected due to the lower bound and upper bound stiffnesses of the backstay. So we have to perform both the analysis, and whichever is giving the larger forces, that we have to consider. Then the bending moment in the shear wall at the base of the tower, that means at the top of the basement, that is also compared. So this is in the upper bound, This is in the lower bound, and this is with our normal stiffness modifier of 0.25. So we can see that, sorry, this 5 is with the fixed base. So we can see in the fixed base condition, it is giving us the maximum, and here it is close, upper bound and lower bound. That much difference as we have seen in the base shear, that much difference we are not seeing in the shear wall, because here it gets compensated. Same thing is happening in y direction also. Now we also try to study the effect of the soil, because in both these models we have not modeled soil, and soil is also expected to provide some rigidity to our retaining walls. So some people may wonder that we have ignored the soil. If soil is present along with the retaining wall, so it will provide additional stiffness. But we have to keep in mind, we also considered the base to be fixed, although we have not modeled the soil by the side of the basement, but we have fixed the base. In real structure, the soil will provide flexibility, so it will provide stiffness to the walls, but it will provide flexibility to the base slab, because base slab will also be flexible. So we made a model where we considered the stiffness of the soil at the base in all the 3 directions, horizontal as well as vertical direction, and on the walls in the horizontal direction. So these formulae which are there in that draft code which we had circulated, and if anybody is interested can write an email, we will circulate. But we have taken this from NCHRP guidelines, and these are the same which are available in NCHRP guidelines. So using these we can calculate the stiffness of the soil. So that stiffness of the soil was calculated and applied at the foundation slab as well as on the basement walls. And with this, when the analysis was performed, so period of vibration, you can see the period of vibration with SSI, that means considering the soil flexibility, and without considering the soil flexibility, you can see the first mode period, it was 2.876 and 2.861. So you can see that this is not having much difference on the period of vibration. And modal mass participation is also varied only little. So that means this effect of the soil is self-compensating, because when we are making a model with fixed base and ignoring the soil, we are compensating for the soil additional stiffness which is provided by the soil at the walls, and some flexibility which is provided at the base. So that model is adequate. Okay, same thing is done for the base shear at the tower base, top displacement. So we can see that the effect is nominal. So there is only insignificant effect which we can ignore. Now another problem which we face very frequently is infills. So in India, we are generally providing masonry infills, unreinforced masonry infills, and due to that, if those infills are provided uniformly throughout the height of the building, perhaps there is no irregularity. But if those infills are skipped in some stories, there is a possibility of infills. But we have to keep in mind that infills provide, although infills provide lot of stiffness and strength, but those fail much earlier. So we did some experimental and numerical study to look at the behavior of the infills, what effect those are going to have on our buildings. So generally we are providing infills after the frame is constructed, and different models are available in literature, either single strut model, double strut model, or triple strut, multi-strut models are available. So we have used single strut model for our analysis. What has been seen in the lab and the past earthquakes, that this strut effect of the infill is able to shear the column. So we can see this is an exterior column, and the infill, which is acting as a strut, is applying a lot of shear force here, and this column is failing in shear here. This is interior column, which is subjected to this strut action from both sides. So when earthquake is from left to right, it is subjected to strut shear here. If it is moving from right to left in the other direction, and you can see that the column has failed in shear. Similar behavior has also been seen in the lab in India as well as abroad. So the problem, or one of the problems which we are having with these infills is that these can cause failure of the columns in shear. So columns need to be designed for extra shear. But what has been seen that all these damages which are seen here, these are non-compliant buildings. If we design the buildings as per our code, what will be the behavior then? This we studied by considering a 4-story building, or sorry, 5-story building. So a 5-story building we have designed as per code, and this portion, because in our lab we could test only a single story frame. So this frame we have taken, but this frame has been analyzed for the full load of this 5-story as per our code, keeping the strong column weak beam ratio. So this frame was taken, and this frame was cast in concrete in our lab, and it was provided with 3 types of infills. So the detailing of the frame was done like this. Special detailing was done at the joints, because we know these knee joints are very vulnerable. Although in the building this type of joints were not there, but because we are testing only single story, so these joints were a problem. So we did not want that the failure should occur at these joints. So special reinforcement as per ACI 318 for knee joints was provided. Rest of the reinforcement in columns and beams was as obtained from analysis as per our code. So it is representing a typical beam column frame of our code. And it was provided with 3 types of infills: the normal burnt clay bricks, the fly ash bricks, and AAC block. So AAC block are lightweight, and these are having less strength also. And 1 brick thick, 230 mm thick, and 200 thick wall with block, and half brick thick walls. Both were tested. So this testing was done in a specimen under, in our lab under cyclic loading, and the cyclic loading was applied like this. Vertical load was also applied to simulate the vertical load being transferred from the upper stories, and horizontal force was applied through this actuator. And this was the hysteretic behavior. So it was seen. So here, this black one is the bare frame. The red one is normal burnt clay brick. The green one is the AAC block. So we can see that the 2 types of bricks have given very close, and all these have resulted in increase in strength and stiffness. So we can see stiffness has also increased, strength has also increased. Ductility is not compromised. We are getting adequate ductility in all the cases. What is seen that initially the infills are providing stiffness and strength, but as the displacement increases, the infills fail, infills crack, those lose their strength, and finally it is the bare frame. So you can see at the final point, close to failure, it is the strength is given by bare frame alone, and infills have failed before that. The good news was that the strength did not reduce below the bare frame. Now we also considered another type of infill which is coming nowadays, that is the EPS core sandwich infills. So that was also tested. So in this EPS core sandwich panel, we are having an EPS panel with wire reinforcement, and then it is plastered from both the sides, 35 mm on each side. So this EPS thermocol, so this thermocol panel, this is providing good insulation, and this plaster is providing strength. And we were surprised that it has given very large strength, and actually we could not fail it in our lab. So this experiment was incomplete. So that's why I have shown it separately. I have not compared there, because we could not go up to failure, and our capacity of our actuator was exhausted. So we have still kept the specimen, and we plan to test it later with a larger capacity system. We also tested these infills in out of plane. because during earthquake, the infills are subjected not only for in-plane forces, these are also subjected to out-of-plane forces. So we tested this in out-of-plane also, and we obtained the hysteretic behavior in out-of-plane. This is the failure mode. I will quickly rush through these. This is the cracking pattern. Now, what you see here, the cracking pattern in plane and out of plane is very similar. In plane also, there is a diagonal cracking pattern. In out of plane also, there is a diagonal cracking pattern. And the in plane damage is affecting the out of plane safety. So if these were not subjected to any in plane damage, these were having sufficient strength to be safe under out of plane. But because an infill will be subjected to in plane as well as out of plane effect both, it will first crack in plane and then it will fail in out of plane action. Now, what we have observed that if a building is designed as per our code, the failure of the beams and columns does not take place. So that which has been seen in the past earthquakes, I have shown you the photographs and the lab, that happened because of the inadequate design of beams and columns. So if we are designing these beams and columns adequately, then we need not to bother about the infills. So infills will be taken care of if we are providing confining reinforcement. As per our code, we are maintaining strong column weak beam ratio of greater than 1.4, then we need not to worry about infills. And the methodology given in IS 1893, where it asks to perform two analysis, one model as bare frame without infills and another model with infills modeled as strut. We make two models, and whichever is giving us larger forces, invariably it is the first model, the bare frame model, which is giving us the largest forces, that is governing our design. And if we design as per that, we need not to worry about the placement of the infills. The soft story phenomena or the failure of the beams and columns due to shear, that does not take place. Even with the strongest type of the bricks, which are available in northern India, at our place we have used those. Those fly ash bricks were also very strong, same strength. In fact, it's slightly stronger than the burnt clay brick which we have used. And AAC block, of course, is much weaker, and it is having much less out of plane force also. But we have to be careful about out of plane. So we cannot achieve good performance in out of plane because these infills are very brittle. These will first crack in plane and then these will fail in out of plane. So if we are concerned about out of plane safety, then we have to do something for ensuring their out of plane safety. But for their in plane action, we have not found the negative effect. All those worries which we were having, that we may have a soft story or our beams and columns may fail in shear, those issues are not there. And we can analyze our building as if as given in the code, and we can go ahead with the design. Then coming to other types of irregularities, one common irregularity which is given in our code is regarding the modes of oscillation in the two principal plane directions. And the code says that the first three modes should have a contribution not less than 65%, and there should be a difference of 10%. Now, this is a big problem nowadays, especially for tall buildings. It's very difficult to get 65% mass participation in the first three modes, and keeping a gap of 10% between successive modes, that is also very difficult. So we perform an analysis because this type of provision is given only in our code. This is not there in any other code. So how important this is, we did. So we considered buildings, different types of buildings, where the difference between the orthogonal directions was different. So one building we used which was square, and in that square building columns were also square. So naturally the period in the two directions will be same. So there will be 0% difference. In another building, we oriented columns in one direction. Most of the columns are oriented in one direction. So the difference in the period was 5%. Then, sorry, here most of the columns in one direction, but the perimeter columns were distributed in the two directions. Here, all the columns are in one direction. And when we do all the columns in one direction, we get a 15% difference. Another building we take where in one direction the bay width is much smaller, so the stiffness in one direction is much larger as compared to the other direction, we get the 40% difference. So we have considered these 4 cases. Then we considered taller buildings where shear walls are provided. The first building where equal number of shear walls are oriented in the two directions, so naturally the period difference is 0%. In another case, we had shear walls in one direction only. We got a difference of 20%. Similarly, here in the elongated direction, we get the difference of 20%. The size of the shear walls is different. Here we get a difference of 20%. So what I mean to say is that the different combinations with different differences we have taken and we perform nonlinear analysis. Now, the code does not give any reason that why there should be a 10% difference. In one literature, we have found, Professor Murthy have mentioned there, that there may be a coupling between the modes and there may be a swapping of energy from one mode to the other. So that may happen in case of coupled mode building where we have torsional eccentricity. So we also considered the building with torsional eccentricity. So all these different types of models, we perform nonlinear analysis. Before performing nonlinear analysis, we calibrated our nonlinear model with the experimental results, especially the shear wall. So in another earlier study, we have calibrated the models for beams and columns. Here we modeled for, we calibrated our model for shear walls, because when we are doing nonlinear modeling in ETABS or SAP, we require these factors. And using these factors as F1, F2, and S, we have to calibrate these models in such a way so that the shape of the hysteretic loop matches with the experimental shape. So we obtained that iteratively, we obtained the values, and those values we have used in our analysis. We performed an incremental dynamic analysis, and what we found that we performed fragility analysis, and what we found that there is not much difference in the performance in all of these buildings. The difference is when we are not considering accidental eccentricity. So if we are considering accidental eccentricity and we are designing these buildings, either way, whatever is the difference in the period, whether there is 0% difference or there is 40% difference, their performance is more or less same, because those have been designed for the same response spectrum. So when we design for the same response spectrum and estimate their performance is very close. Hardly any difference in the performance is there. Or in other words, the logic of these clauses in the code is not clear. Why those have been provided? Because we did not see any swapping of energy or any problem with those buildings which have been designed with 0% difference. Bisymmetric building, we are calling them. The buildings are having same period in the two directions. And there is no such provision in any other code. But more studies are to be done. Some more people will do these studies. And then we can come to a consensus that whether this 10% difference clause is required or not. Till then, you have to go ahead with that. You have to maintain that. Then another type of irregularity which we have investigated is this torsional irregularity. And in torsional irregularity, there are two issues. One is the eccentricity of mass and stiffness, which we call stiffness eccentricity. So we can calculate the center of stiffness and center of mass. And if center of stiffness and center of mass are not coinciding, then the building will have larger interstory drift, larger displacement on one side, which we call flexible side, and on the other side it will have a smaller interstory drift or stiffer side. We can call it rigid side. We can call it. Another issue is that the building may be perfectly symmetric. so that the center of stiffness and center of mass are coinciding, but it may be torsionally flexible. Torsional flexibility means that its torsional rigidity is smaller as compared to its lateral stiffness, and that will be reflected by its torsional period. So if the torsional period of the building is longer than its lateral period, translational period in X or Y direction, then it is torsionally flexible. The problem with torsionally flexible building is that due to any region, if there is a torsion applied, that torsion will get amplified significantly. So it will have large torsional response even under a small torsional movement. So that is to be avoided. And different codes provide different guidelines for that. So we have compared also the guidelines of different codes. IS 1893, of course. AC 7 has recently changed its guidelines. So in 2016 and 2022, there is a difference. The New Zealand code, European code also has this. And these guidelines are provided in two ways, or in terms of two parameters. One parameter is the maximum displacement by minimum displacement, or maximum displacement by average displacement, and E by R. E is the eccentricity. So Eurocode provides in terms of totally different parameters. E by R. So E is the eccentricity between the center of mass and center of rigidity, and R is the radius of torsional rigidity. So torsional stiffness K theta divided by Kx and a square root of that. That will give us this rigidity. And it gives the limit in terms of ratio of E by R as 0.3. The flexibility check is in terms of the period. So rotational period to translational period. So it is T lateral by T rotational. So lateral by rotational period should not be less than 1. Should be less than 1, then the building is not torsionally flexible. If lateral period is longer than rotational period, that will mean that the building is, if rotational period is longer than the lateral period, then the building is torsionally flexible, otherwise not. Eurocode provides this check also in terms of R by L. So R, as I explained, this is torsional radius of torsional rigidity, is square root of K theta by Kx or Ky, and L is the dimension of the building perpendicular to the earthquake direction. So R by L, if it is less than 1, then also it is treated as torsionally flexible. So different codes have different requirements. Our code does not allow torsional irregularity. So if the torsional period is smaller than torsional period is longer than the lateral period, and delta max by delta min is more than 1.4, then our code does not allow that building. It is prohibited. And along with the torsional irregularity requirement, accidental eccentricity is also prescribed by different code. Our code prescribes 5%. American code also prescribes 5%, and it allows buildings with torsional irregularity. If the torsional irregularity is more than 1.2, that means delta max by delta min is more than 1.2. It provides amplification. It asks for amplification of accidental torsion. And if it is greater than 1.4, then it causes a redundancy factor. It applies a redundancy factor. Redundancy factor we can think like reduction in response reduction factor. So response reduction factor is reduced by a factor of 1.3. New Zealand code does not have any clause regarding torsional irregularity. It only says that the torsional eccentricity is to be considered as 10%. Eurocode causes a reduction in response reduction factor. It fixes the maximum response reduction factor for ductile buildings as 3. So from close to 5, it reduces it to 3. The accidental torsion is same as in our. Now, the revised code, which is in wide circulation, IS 1893, which is yet to come, or which is under wide circulation, which we may be discussing in some future talk. So, there both torsional irregularity or eccentricity and flexibility both are considered together. So there is a combination, a matrix is provided on torsional eccentricity, that is Ek by V. This Ek is nothing but the distance between center of stiffness and center of mass. And V, as we have been using earlier, this is the dimension of the building perpendicular to the loading direction of earthquake. So ratio of Ek by V, and T theta by Tx. T theta is rotational period, Tx is the translational period in x direction, Ty is the translational period in y direction. So T theta by Tx cannot be greater than 0.9. That means at least 10% difference. So T theta has to be smaller at least by 10% than Tx and Ty both. So this maximum value is 0.9. And then depending upon how much is the eccentricity present, this value of T theta by Tx is allowed. So if this T theta by Tx is 0.6, that means the building is torsionally very rigid. Then the maximum value of Ek by V allowed is 0.125. More than 0.125 is not allowed. That means 12.5%. And we have to understand 5% is accidental eccentricity itself. So accidental eccentricity itself is 5%, and total is 12.5%. So this matrix will come into force when this code is published. Okay, so we also did a study on torsionally irregular buildings. So one building here you see it is torsionally rigid because the shear walls are provided along the perimeters. So its torsional period is less than 10% of the translational period. Same build configuration by keeping the number of shear walls same, but changing the location of those shear walls. Shear walls are shifted towards the center from the perimeter. So here we can see that this becomes a torsionally flexible model, but it is still symmetric. So eccentricity is not there. This is a torsionally irregular because one of the shear walls has been shifted from perimeter to this, but it is still not torsionally flexible because other shear walls are at the perimeter. So still T theta is less than 0.9 times Tx. And this is a torsionally irregular and it has irregularity in both the directions. So eccentricity is there in both the directions. Now, if we look at the effect of torsional flexibility and irregularity.
Sir, do you want to take a short 5-minute break? It's already 2.
I'm just finishing in 5 minutes, less than 5 minutes I will finish.
Okay.
So I don't want to take you into these details. I just want to discuss the final outcome. And the final outcome is that both torsional flexibility and torsional irregularity, that means eccentricity, are important. And when we are designing our buildings, we should consider both. Both we should take into account. And this revised code through this matrix, it will provide limits on both. Last thing which you may be interested is this floating column. Many times we have to discontinue our columns, and again different codes have different guidelines. Our code, New Zealand code, Euro code prohibit, whereas American codes, ASC 7 as well as this Tall Building Initiative code, these are permitting. So American code is permitting floating columns, but it says that the structural members which are supporting that floating column, those should be designed for higher forces, and that higher force should be over strength times. So those who are familiar with ASC 7, they know that tables are given in ASC 7 where over strength factors are given. So the forces need to be increased by over strength times. Similarly, this Tall Building Initiative document, that is also increasing the forces, but this is increasing by 1.5 times. So it says that you increase the forces by 1.5 times. Now, in case of floating columns, what we have observed that effect of construction sequence, that becomes very important. And to illustrate that, there are two or rather four models we have considered here. These two models you see, this is the regular model or what we call baseline model, where all the columns are continuous from bottom to top. Here in the ground story, these columns have been removed and these columns are starting at the first floor level. So these becomes floating columns, and these dotted beams, these become transfer beams. So you can understand these transfer beams are cantilever beams, so these will be subjected to larger moment, and these should be designed as transfer beams. Another model, we removed these two columns on the face, so interior columns in the exterior face, those were removed. So this column and this column, similarly here and here, those becomes floating columns, and these dotted beams, these becomes transfer beams. Here, all the columns here and all the columns here were removed. And then two studies were done. In one study, the columns in the ground story were removed. In another study, the columns in an intermediate story were removed. So floating columns starting from first floor, floating columns starting from an intermediate floor. Both studies were done. Nonlinear analysis was performed. I will skip. The most important thing which we discussed, which we found was that this construction sequence. So in construction sequence, generally what we are doing, we are performing a simultaneous analysis, where we assume that whole of the building is constructed simultaneously. But in reality, that does not happen. Building gets constructed sequential. So we follow that sequence in analysis. When we are applying the first floor load, only the single story is present there to register that. When we are applying the second floor load, then two stories are there, then three stories, and so on. So this is the sequential analysis. And if we perform sequential analysis on a regular building, low-rise regular building, two-story building, if I perform a sequential analysis, then there is hardly any difference in the bending moment. You can see this is the bending moment in column, 12 kilonewton meter, 13 kilonewton meter, hardly any difference, because it is a small building, two-story building, and regular baseline building, no floating column. But even in this two-story building, which is very small, if I remove a column and perform sequential analysis, then you can see how much difference is there. So this is 237, this is 444. So huge difference, double moment we are getting. So sequential analysis becomes very important when you are having a floating column. Do not forget to do sequential analysis, even if your building is very short, very small building, and you are having a floating column. Do perform sequential analysis. Otherwise, it is not earthquake. It is the dead load and live load which will fail your columns. Okay. So if you look in the, this is eight-story column. If you look at the bending moment in the columns, this is for regular building column. So the columns with the moment in the column with sequential and simultaneous analysis, not much difference. But if you look at the floating column, okay, FC2G. So this is the one where the ground story column has been removed. So here you can see high bending moment occurs, and the sequential analysis is giving even larger bending moments. So you can see that sequential analysis is giving larger. This is the hinge pattern under earthquake loading. And what we have seen that if we are properly designing the building considering the code, even without increasing the load on the transfer girders by 1.5 times, if we are designing as per our code by following a strong column weak beam ratio of 1.5, we get the desired failure pattern even where we are having floating columns. So what was undesirable, that hinges should not form here in the beam. in this transfer beam. If the hinge was forming in the transfer beam, then this beam will collapse. But the hinge should form in the column. This is important. In the floating column, the hinge should form, because if the hinge is not forming in floating column, the hinge will form in the transfer beam. And if this transfer beam or transfer girder is developing a hinge here, the building will collapse. So we have to ensure this location. So one clause in our code, which is quite misleading, it says that lateral load resistance, the floating column should not be considered. That is actually counterproductive, because what people do, they release the floating column at top and bottom so that it does not participate in the lateral load resistance. And as a result, when it is released, the bending moment which you are getting in design at your transfer beam, that reduces. And then there are chances, because in actual design, actual construction, there is no release here. So it will cause failure of the transfer girder here, which may lead to the collapse of the building. So it is important that we do not release this column, and we design for whatever forces are there, and we follow ductile detailing, including strong column weak beam ratio of 1.4. Then for these buildings which we have analyzed, we do not see any failure. And of course, when we are using American code or TV guidelines, then it is further ensured. So we can use floating columns, provided we are performing a sequential analysis and we are properly designing our transfer beams. So it has been seen in all the cases that it works fine if the collapse margin ratio is sufficient, and our building will be safe, provided, again I am underlining, we follow construction sequence analysis. That is very, very important. Thank you. That's what I wanted to discuss in today's task. And although I have taken a slightly longer time than originally planned, but I have covered everything which I have planned. Many times I had to stop in between because of the shortage of time. So thank you very much for being patient for these 2 hours and sitting, joining, keeping with me. Okay, so now we can take up the questions.
So, thank you, Doctor. Wonderful presentation. We'll take up question and answers.
And shall we give 2-3 minutes break so that people write questions, and sir also will get some time, I think.
Okay, so we can have a 5-minute break.
Yeah.
And then we will join again.
No problem. Okay, shall we start?
Not on the place. Yeah, I think we should start with there.
Has Professor joined?
Yeah.
Yeah, okay. So,
Um,
okay, so we'll take up questions one by one.
Okay.
So before that, there's one small, very basic question, and that is for the benefit of all the junior engineers, because most of them have a doubt in their mind whether they should model this combined shear walls like C shape, L shape, or T shape of shear walls as with a single pier level or with multiple pier level. And is there any difference in the sharing of the forces?
Actually, there are two issues here. One is the modeling and another is design. So modeling can be done either same pier or separate pier. So like I said that if there is a C-shaped shear wall, we can assign separate element to web and separate element to flange, and we can interconnect those using rigid elements. But when we are designing, then it is to be designed as single pier. This is important. The whole C shape will act as single member. So whatever forces I will be getting in these three columns, those three column forces I have to integrate and get as the total axial force, bending moment, and shear force acting over the whole section. When we are using finite element, shell element for modeling, I can do meshing, and that meshing will take care of the shape. But when I'm designing it, then this C shape is to be taken as one pier and it's to be designed together.
Thank you. So we start with the first question. In some literature, it was stated to assume some columns as gravity columns and design. But as per my understanding, they shall be made gravity columns by making them only to take gravity loads. Then why codes and draft standards are setting to assume some columns as gravity and design?
Yeah, there is a lot of confusion. Very important question. There is a lot of confusion regarding gravity columns. So what is a gravity column? So gravity column is not the one which we declare as the gravity column. The gravity column is the one which is taking almost only gravity. Now, how a column will take only gravity load, not the lateral load? Because its lateral stiffness is very small. So lateral stiffness will be small by two ways. One is that it is the size of the column itself is small, so stiffness of the column will be small. But in that case, it will not be able to take gravity load also. But if it is not connected through beam, it is not having a frame action, it is connected through slab alone, or the size of the beam is small, or the span is large, then the lateral force it will attract or the bending moment due to earthquake will be small. In that case, we can design our column in such a way, we can afford to design our column in such a way that it will remain elastic during earthquake. So it will remain elastic during earthquake only if it is attracting much less force. That means rest of the structure is having sufficient number of shear walls, intrastory drift is limited, and this column is connected through flexible beams with the rest of the structure, so that much lateral force or bending moment due to lateral force is not much, and we can design this without using response reduction factor. So if we can do that, then that is defined as the gravity column. And advantage we get is that because it is not yielding during earthquake, then it will, we need not to do the ductile. That's it.
But we will have to.
What people misinterpret this is that any column they declare as the gravity column, and then they say we will not design it for earthquake. So that is not the correct way. This is not our choice. This is the behavior of the column which will decide whether it is a gravity column or it is lateral load resisting column.
And at the same time, it has to satisfy the displacement compatibility clause.
Yes,
for
displacement compatibility, when we are
doing this R is equal to 1, actually we are following the displacement compatibility. Yeah, right. So if we take R is equal to 1, that means the full displacement will be applied on that, and it should remain elastic. Elastic, it should be designed for those forces which will occur at R is equal to 1. So we go to the next question. Mr. Kunal Talsania, he has asked this question. Do we need to assign upper bound and lower bound stiffness modifiers to ground floor beam column slabs and walls, or all substructure floors, that is the subsequent basement floors? It should be done for all the basement, not only slabs. Our code says also the shear walls, retaining walls. So retaining walls and slabs, all the retaining walls and slabs of the basement should be provided with these upper bound and lower bound properties. Okay. The next question is for performance-based design, displacement is to be verified. Then coupled approach may be suitable. In this case, how to adopt a simple model? I mean, there is no simpler model than what we have done. At least you have to model the basement with its walls. You can avoid soil because soil is not having much effect, as we have seen. So you have to model fixed base basement with its retaining walls and the tower. So that much is to be done. The next question is for approach 1 modeling. Can't we consider at least one grid extra all around the tower area to consider actual gravity loads on periphery of tower area, shear walls and columns? We can do that. That will not make much of a difference if it saves you with some modeling issue, because the gravity load, otherwise you have to apply manually. So, but just hold on, When I'm saying modeling of tower, we are not modeling that portion of the tower below the basement. We are modeling above only. So there is nothing, and by the side of that. So we are fixing at the top of the basement, ground level. So there is no sideway way there. There is no other column there. And rest of the portion below that level, we are modeling separately. So their full model in any case is there.
This question is asking is about when we do the complete model up to foundation and do a single way around to transfer vertical loads. So is that a correct method?
When we are modeling the complete model, then whole basement we are modeling. Generally, what people are doing, they are modeling the tower right up to the foundation. Yeah. That is incorrect.
That is incorrect. That's what.
That is incorrect. The tower is to be modeled up to the top of the basement only. Okay. The next question is for combined model tower plus non-tower area along with the retaining wall. Ideally, we should keep stiffness modifiers of retaining wall as 0.001 as low as possible. Otherwise, all base shear will be attracted by retaining wall only, and building will have less shear. No, I couldn't get. He is talking about coupled model or first model? Coupled or
I think it's coupled model. Coupled model. So in coupled model, we are doing stiffness modifiers using upper bound and lower bound sensitivity analysis. So that we have to follow. So whatever stiffness is there, or loss of stiffness is there, that will be taken care of by taking these factors as 0.5 and 0.15. There is no need to perform an analysis with 0.001. Yeah, but that, yeah, right, because that will be actually the against the actual behavior. So whatever is code specified, we should follow that.
That will be conservative for building foundations. That is the only thing.
Correct.
That will be conservative for the building foundation. That's correct. Building foundation in the tower portion.
Tower
But that is not needed. That much conservatism is not needed.
Okay, next question is, what are the latest advancements in seismic retrofitting techniques for high-rise buildings? So it is completely a different topic,
Yeah, this
and
is the
we can
topic
we can deal with this topic in separate webinar or seminar. The next question is, in IS 16700, table 5, crack section properties of RCC members, stiffness modifiers are applied to moment of inertia. Why these are not applied to the cross-sectional area?
Generally, in vertical direction, our structures are very rigid. So stiffness in axial direction, in any case, is very high. It is very difficult to get vertical mode of vibration. That's why these are not applied. So whether we apply or we do not apply, in any case, in vertical direction, we are doing static analysis. If we look at our code, SAYG value is taken 2.5. So that is not there. But if the question is regarding shear area, then there we have to keep in mind that there it is applied.
Okay, the next question is from Mr. Pranav Rajendra, but I don't think the question is quite clear. What about type of soil? Probably he means while carrying out soil structure interaction, how the soil is to be treated. But I think we will be able to capture the soil properties and accordingly.
Actually, when people talk about the type of the soil, one thing they forget that the foundation will be designed for that soil. So they keep the foundation size same and make the soil flexible. That is not possible. If there is a weaker soil, the foundation will also be larger. So stiffness will increase. So soil effect, mostly in most of the cases, the soil flexibility effect can be ignored. Code also says that. Not our code, but if we look at LA, TBC, and NCHRP, in most of the cases it can be ignored.
The next question is a request to share soil structure interaction model for study purpose.
Okay, so the model which we have done, you want to, so please write an email, we will share.
Okay, the next question is, in tall buildings with basement having transfer structure, the soft story effect is observed at transfer level. The reason is distributed wall, high stiffness in tower, but column have relatively low stiffness provided at transfer floor.
It's not.
What are the remedies to overcome this soft story issue observed, or different calculation methods are used for both to calculate story stiffness? I think
there are two issues here.
Yeah.
One issue is that if we are providing a transfer girder very deep or wall, the stiffness of that story, lateral stiffness of that story will be very large. So that we can ignore. That issue is not here. We have to only ensure that the story below that should not develop column sway mechanism. Hinges should not form in the column. So for that, we have to follow a strong column weak beam ratio of 1.5. So whatever is the stiffness of that transfer girder, whatever is the strength of that transfer girder, 1.5 times of strength is provided in the column sway. So those columns are much stronger. So that phenomena of soft story or weak story will not occur if we are following the strong column weak beam ratio of 1.5. In case of a shear wall being transferred, there will be one story deep shear wall, and then it cannot be supported on columns. We need to support that also on shear walls, which are at least 1.5 times stronger than this transfer wall.
Right. Okay, the next question from Mr. Prasad Adhav. Would maintaining a strong column weak beam ratio of 1.4 result in provision of almost square columns? Not necessarily.
Rejects in a square column.
Pardon?
Sorry, I could not get the question. Can you please repeat?
Question is that would maintaining a strong column weak beam ratio of 1.5 will it result in provision of almost square columns?
No, it depends. It depends on what are the beams connected in the two directions.
Yeah.
So in each direction, we have to ensure a strong column weak beam ratio of 1.4.
Okay. The next question is real-time dynamic analysis possible?
By real-time dynamic analysis, perhaps he or she means that as earthquake is coming, with the same speed our analysis is done. So that is not possible. So far, we need a very efficient algorithm and also a very high speed computer for that. So I don't think currently it is possible.
The next question is regarding the new time period formula that is added in IS 16100 2023 edition.
We'll
Please
be taking
throw
a separate lecture on that. Like next 20th July is the separate, that is full topic on that only.
Okay, but
Yeah,
by the
but
way, what is the question? We can say if we can.
Yeah, he's asking, please throw some light on this formula.
Well, again, these formulae are also based on the judgment of the court committee. And you know, judgment is not always supported by rational or adequate studies. Judgment is judgment. So these formulae are also based on judgment. I have not seen any detailed study which is supporting these. So it is something like we decide, we take a combined decision that we will be designing our buildings with this much, because this is one way of providing some reserve strength to our building. So we decide that this much reserve strength we will provide to them. That's it.
Next question is with buildings designed with floating columns, is it necessary to follow a strong column weak beam design philosophy? Yes, this is already answered.
No,
Next question is
here there is a catch. At the floating column, no. The floating column has to be weaker than the transfer gutter. But those columns which are supporting the transfer gutter, those have to be strong. So not that the floating column should also be stronger than the transfer beam. No. Because as I have shown, the hinges should form in the floating column, not in the transfer gutter. If the hinges form in transfer gutter will collapse. So at the junction of floating column and transfer gutter, it will be strong beam, weak column. But at the junction of transfer gutter and supporting columns, it will be strong column, weak beam.
okay. How to detail the junction of floating column and transfer gutter in RCC?
I mean,
So
in same
we will have to follow this.
as we are,
Yeah.
I mean, this transfer gutter is acting like a foundation. So the way we detail at the foundation level, same detail. Follow.
I think probably he means whether we should follow ductile detailing.
Ductile detailing is to be followed. So 13920 provides detailing of columns at the foundation also. So this transfer gutter is like a foundation to that column. So same we can follow. The vertical reinforcement will go LD, and at least 300 millimeter inside we will provide a special confining reinforcement.
So the next question is there is a suggestion to arrange a separate seminar on soil spring modeling in ETAF and practical. So we'll definitely consider.
It's a good idea. Maybe for next webinar or this, we can do
that. Can you shed some light on design of RCC structural walls with regards to slenderness moment? What are the requirements as per our Indian codes?
Our Indian code actually does not take into account the slenderness effect. So minimum thickness in outer plane is given, and that's what is assumed to take care. But I will suggest that you go through ACI 318 requirements. Our code provisions on shear walls are highly inadequate, very, very inadequate. So we should follow ACI 318 or Euro code.
Okay, can you provide more information about performance evaluation of vertical irregular buildings? Vertically, wherever there is a vertical irregularity in buildings, how the performance is
No,
evaluated.
we have discussed some of the
Yeah,
vertical
very.
irregularities we have discussed, and we have seen which are the factors which are affecting and what precautions we can have to avoid deficiency in the performance.
Okay. The next question is regarding these infill walls. Can you share sandwich panel properties? Do you have any results for acceleration and displacement sensitivity analysis?
Not yet. We don't have those details. So we have only limited information about those. Maybe when more research is done, those properties may be available.
How ground motion selection can be done for irregular structures?
Ground motion selection does not really depend upon the
type of
except the dynamic characteristics. I mean, we have to take into account the period of vibration of the building. So in that sense, only structure counts. So it is mostly based on site. So source that is governing our site, those source characteristics and the site. These we have to take into account when. But it is a topic in itself. In one of the previous talk, I think we have talked about that a little. Maybe sometime we can talk in more detail. But we are mostly focusing these talks on professional offices, design offices. There, people are still not doing much time history analysis. In case people start doing time history analysis, we can do that. For researchers, we are having separate courses, and those who are interested in ground motion selection, scaling, spectral matching, we are having separate courses for researchers. You can join them on ground motions.
Okay, thank you, sir. So next question is, sir, how significant is the model mass participation factor value in seismic analysis? Also, how to increase the value in the initial modes of the analysis?
Actually, there is no way in which you can increase. There is no clear way in which you can increase. If your building is regular, model mass participation will be higher. If the building is irregular, modal mass participation will be lower. But in my personal opinion, it is not such a large issue of concern as long as you are considering 90% mass participation. If you are considering enough mode with 90% mass participation, or if you are not able to perform a time history linear time history analysis, that is good enough. So our code puts a lot of emphasis on 65% mass participation in the first three modes and 10% difference in the period. Personally, I don't think that is required. And maybe we can raise this issue to the code committee. So from your respective fora, if we send that this is not there in any other code, there is no known basis of this. So code committee may reconsider this clause, the 65% clause. This is creating a lot of trouble to our designers. It becomes very difficult in case of tall buildings to get 65% mass participation. And there is no known benefit of that. What we are achieving with that, it is not clear.
Okay. The next question is, I think, regarding Maiwan. It means the monolithic construction where the internal partition walls or sometimes the external walls, partition walls are exterior walls are constructed with RCC walls, as constructed as RCC walls. So he's asking a question: should we use Maiwan wall stiffness and how should we model Maiwan wall in a test? Maiwan wall is probably a non-structural RCC wall.
So these so-called non-structural walls, there is no guideline available. No testing has been done. Even in research literature, I was searching, there is nothing available. Very few tests have been done on some walls. They call thin walls, but their thin wall is also 150. So that is our structural wall. So no literature is available on 80, 75 or 100 thick wall. So it is very difficult. First testing is to be done. And there is nothing like non-structure which we can ignore. RCC, we have done this test on this EPS core sandwich panel. So EPS core sandwich panel, we have only 35 plaster with wire mesh reinforcement on two faces. And we could not break it with our actuator facility available. So it is having huge strength. So
here it is monolithic also. Here it is monolithic also.
Here it is monolithic also. So I do not agree that anything is non-structure. It is a structure. But how to model it, how much strength, stiffness and ductility is available, for that we need testing. And once testing is done, then only. So currently, when we are designing and constructing Maiwan buildings, either we do it as shear walls, and we are doing a lot of gambling there. We do not know the behavior. Still we are designing.
There could be serious underestimation of the time period.
If you design it as a shear wall provisions will be applicable. Now, that is not possible to detail them.
No, I mean, if the stresses are low, then ductile detailing confinement may not be needed. So code also permits single story. So I mean, single layer reinforcement. But then the stresses have to be sufficiently small. And the most important question is, what should be the response reduction factor for such building? That is not known. So no study is there. We can't use 4 because that is for ductile buildings. That type of ductile detailing we are not doing. So what, in my opinion, it can't be more than 3.
The next question is from Raju Pudari. Sir, if we use dampers in earthquake RCC resistant structure, if the cantilever beam is there for portico area 15 feet, what are the considerations taken when we design peripheral column and beam junction areas?
It appears to be a very specific problem. I'm not
Yeah.
able to visualize.
Yeah, it's a
so
sort
please
of a
write
case.
to me with the details.
Yeah, it's a lot of a case
And
study.
we can discuss, because I need to really visualize what you are talking about with drawings. So please share some sketches and then we can discuss.
Okay, the next question is from Ishtiaq Haradwala. If we have building which all base shear will take by shear wall, and on that building there is 2 to 4 columns which we design for gravity column. So for that type of structure, shall we check building for deformation compatibility?
Yes, deformation compatibility is to be checked in any case. So this will be designed as shear wall only building. Corresponding response reduction factor we will take. There is no need for, of course, that cannot be done 25%. And if there are shear walls, these columns will attract very little force, and there should not be any problem designing these for displacement compatibility. That means R is equal to 1. Columns will be designed with R is equal to 1, and shear walls will be designed with the corresponding response reduction factor.
Okay, there is a request to repeat the answer of first question about pier level, that is separate or combined pier level. Maybe he has missed it.
In design, the one cross section, okay, the portion of the shear wall which is physically connected, that is to be defined as one pier. So if it is a C-shaped shear wall, or the example which I have taken where there were 2 C-shaped shear wall connected with coupling beams at the 2 sides. So each side, each C-shaped shear wall will be defined as one pier, not as 3 piers. most of the times what error people are doing in industry are that valve they are defining as a separate pier, flange they are defining as a separate pier. So we cannot separate out valve and flange. So valve and flange, which are acting together in the physical structure, should be defined as one pier.
Okay, the next question is from Mr. Arjun Kumar Bajaj. He's from Roorkee. Sir, could we talk a little about foundation load calculation in column support reaction? What load combination need to be taken and with what multiplying factors? Is IS 1903-2021 dictates about unilaterally load factor, but many structural engineers take that worst loading combination, which produces maximum load on building. Is it correct?
There are two questions here. One question is related to the load factors. So load factors depends upon which design method we are using. If we are using working stress method, then we have to consider serviceability level earthquake. And there the load factors will be unity, one. If we are using now foundation codes are also have been revised and those are also based on limit state method. If we are using limit state method, then DBE level earthquake force is to be used. That means a factor of 1.5 is to be used. I have repeated this in earlier. I think it is worthwhile repeating here also that the factor of 1.5 which we are using in our code is actually not a load factor. It is a correction factor for making serviceability level earthquake to design basis level earthquake. So when we are not using 1.5 factor on our earthquake force, it is serviceability level earthquake force. When we are multiplying it by 1.5, then it becomes dB. And when we multiply it by another 2, so that means 1.5 into 2, 3, then it is MC. So if we are using limit state method, we have to use dB level force. If we are using working stress method, because in working stress method, factors of safety are larger. So there we are using serviceability level. So that is regarding the first point. Second is which load combination which we have to use. So currently our design philosophy is that the foundation has to be stronger than the structure. Hinges should not form in foundation. Hinges should form in structure, column base. So actually our code still does not talk, but we should follow capacity design. The foundation of the capacity of the foundation should be more than the capacity of the column. So considering the burst combination is definitely needed, but even that is not sufficient. In future, our code will do that. So we should also go for capacity design. Actually, in bridge design codes, that is already there. So in bridge design, when we are designing a well foundation, we first calculate the moment capacity of the pier, multiply that by 1.35, and then use the foundation or design the foundation for that amplified this. This is still not there in building codes. I hope in future it will come.
Yeah. The next question is while modeling the retaining wall, is it necessary to apply soil pressure?
No, during analysis of building, it is not needed. But when you are designing the shear wall, then in that case, you have to design it for in-plane as well as out-of-plane forces. Out-of-plane force will come because of the earth pressure.
Okay, the next question is how to compare performance of different vertical irregular buildings.
There are methods. Here, SC41 provides that method. So actually, it is a separate topic of performance-based design. Difficult to explain in answering to one question, but I can say this. Performance of different structures, whether regular or irregular, is compared in three terms. One is plastic rotation in members. So we will calculate plastic rotation in beam, column, shear wall. Limits are given in SC41. So we will compare with those limits. That is one criteria. Another criteria is interstory drift. So we will calculate nonlinear inelastic total interstory drift, and we will apply criteria. Third is floor acceleration. So another criteria, especially from the point of view of non-structural components, when we are designing a hospital building. So their floor acceleration can also be important. So in terms of these three parameters, we can compare performance of any two buildings, whether regular or irregular.
Okay. What is the reason ETABS is preferred over STAD software for analysis of RCC buildings? So
No.
it's a very subjective question.
No preferable software. Any software which can serve your purpose, you use that.
There is a request to share recording of this event. Yes, we are going to share it. How to draw fragility curve for performing non-linear time history analysis. So again, it's
fragility curves are not required for non-linear time history analysis. Non-linear time history analysis is required for fragility curves. So generally, people do not. I mean, in design we don't use fragility curves, so that is not needed. Only in research we are doing that. So it's important to learn non-linear analysis. For the time being, you can skip fragility curves. That is not much use.
okay, there's a question, a request for engineers starting their career. Can you please suggest some study material for dynamic analysis and basics of FEM?
Yeah, there are several books. So there is not one book, but there are several books. I can prepare a list and share. I think that's a good idea. We can share through Epicons also.
Yeah.
Anybody who wants to go for practical design, starting the career, what is the minimum thing which one should read?
Okay. For coupled shear wall having the story of 34-meter height, a 30-story building probably means. What is the wall thickness we should keep at the site, and what type of brickwork should we construct to minimize self-load on the structure? So,
See, minimum 200, desirable anything above 500. Code permits 200, but I personally do not agree with that 200. It should be more than that.
Okay, the next question is, which loads cause out of plane loads in infill wall panels?
Earthquake and wind, because earthquake is in both the directions, and wind pressure can also cause out of plane.
Okay, what is the DD and LL ranges design load into factor of safety should be taken in design of earthquake resistant structures?
I couldn't get.
Yeah, this question is not clear.
DD must be dead load. Dead load is but
no, he's saying design. Okay, dead load and DL and LL. Okay, design load into factor of safety. So that's code prescribed. Actually, you don't have to.
Partial factors of safety are given by the code. We have to just use those.
When deep beam is resting on narrow side width of a column, then how to satisfy strong column weak beam theory?
Only by magic. Practically, it cannot be done. So you have to avoid such situation.
Avoid.
The deep beam has to rest on wide column. That dimension of the column has to be large. Otherwise, you can't satisfy it.
Okay. Does flare column is different from floating column, and if does, then what is the effect of earthquake on this column? A splay column or a flare column, a column having a varying
splay at the top.
Splay at the top, varying depth. Yeah.
Varying size. So generally that is done in case of flat slabs. I don't think it is done in beam column frame also. It is done.
Yeah, frame also people are using it sometimes to create a space at lower levels.
Yeah. Now, in many places you have to satisfy the municipal regulations where you have to leave some open spaces. So the columns have to be placed little inside, and then they have to be flared to match the building face at the upper floors.
So you mean that column is vertically shifted?
Not shifted. It is sort of the size is increased towards the top. It's a tapered column.
Tapered column or inclined column with a certain minimum slope. not suddenly, but some slope is taken, and then suppose bottom size is say 300 by 600. After first floor, it gradually increases to 1000.
So the base level, the size of the column is, let's say, 300 by 600. And when it touches the first floor, it is 300 by 900. So it's tapered from the base level, ground level to the first floor level.
And what is the size of the first floor column?
300 by
It
900.
continues, then further the bigger column continues.
So in the bottom story, the size of the column is smaller, and in the upper story, the size of the column is larger.
Gradually, not suddenly, but gradually.
Yeah, but gradually, but it is like that.
Yeah.
So I do not know whether I have fully visualized the problem or not, but it appears to be very dangerous thing, because column stiffness and strength should reduce along the height, not increase. Otherwise, it will become a weak story problem. So somehow you have to avoid formation of hinges in the lower story. So that is difficult. For that, at least nonlinear analysis will be needed, or you have to design with R is equal to 1. So that column, the weaker one, is to be saved. Hinges should not form there. And with this type of arrangement, what I am able to visualize, it appears that the hinges will form in that column, which is at the base. And not only that,
level.
because of the eccentricity, there is the center line of the upper column and the center line of the bottom column is not matching. So there is an eccentricity. So there is lot of moment will generate in this bottom column. So such situation is to be dealt with very, very carefully. That's what I can say. I am sensing problem here.
The next question is, what is the difference between stuck column and gravity column not starting from base?
What is the stuck column?
Floating column, probably, yeah. So he probably wants to know difference between a floating column and a gravity column. How these two to be treated in a similar way?
No, both are different. Floating column, I mean, gravity column is starting from the foundation and going up to the top. Floating column is starting at an intermediate level. Floating column has to be supported on transfer girder, transfer beam, and that transfer beam has to be designed strong enough so that it is stronger than the column it is supporting. And at the same time, the columns which are supporting the transfer beam, those have to be stronger than the transfer.
The question is not clear. Mr. Istiaq Radwala, he has asked a question in continuity to his previous question, that his question was previously, when the building is designed with shear walls, are the remaining columns, whether they need to be designed checked for displacement compatibility? The answer was yes. But the question is, I think the same question is asking about, we have to check deformation compatibility, or we have to design with R equal to 1 because all forces are taken by shear wall.
Both means the same. R is equal to 1 is deformation compatibility.
Bajaj says, sir, could you take my second question, please? I don't think it is possible because we have moved ahead. Mr. Sutar is asking a question where, what can be the effect of soil flexibility if considered in model in case of no basement?
In case of no basement. Okay, in case of ground supported building, also soil flexibility has a small effect. So soil flexibility will elongate the period slightly, almost similar effect what we had in this case. So there is not going to be a drastic effect on the building performance.
Next question is coming up from Mr. Vinayak Naik. Can we use a combined superstructure and substructure model with no mass for substructure to determine base shear and then match the base shear as per the empirical formula for superstructure? instead of having a separate superstructure model to determine the base shear?
We can do that. That is possible.
Okay, the question is regarding latest advancements in seismic retrofitting techniques for high-rise buildings. So I think we have already answered this question. There will be a separate, it's a separate topic for a webinar or seminar. So we'll be considering this request. If we model retaining wall, then earthquake applied above the retaining wall level, it is correct method or not? Okay. The question
perhaps
is
what he or she means is that no earthquake need to be applied below the soil level, something like that. No, that's not correct. The portion which is below the soil, that will also be subjected to acceleration, and the forces need to be considered on that portion also.
okay. The question is, sir, we have to check all models and torsion irregularities with property modifier of strength like 0.7 for shear walls and columns and 0.35 for beams as per 1893. We have to follow 0.9 and 0.7 modifier for service model. Is it a question or it's a note? I don't know.
I mean, that is correct. Whatever is stated here is correct.
Sir, in earthquake resistant structures, can we use dampers? If we use them, how they will work?
Okay, that's again a topic.
Yeah, right.
We can talk maybe about dampers. So dampers is a topic in itself. We can definitely use.
Question is, sir, in a 7-story building with stilt parking, is there no need for providing infills in stilt level? Mr. Arjun Kumar Bajaj from Roorkee is asking you a question.
Yeah, there is no need to provide infills, provided we are following a strong column beam ratio of 1.4 and doing the time.
Please elaborate importance of design eccentricity as per 1893 and application in analysis.
Design eccentricity. Perhaps that formula which is given in the code ED as 1.5 ES plus 0.05 and ED as 1 times ES minus 0.05. So yes, that formula, but how to explain its importance, that is to be followed. We have to use that eccentricity in our analysis. But yes, when you are doing a 3D, normally we do a 3D dynamic analysis. Problem is there. So in 3D dynamic analysis, this 1.5 ES or ES part will automatically come in our analysis. Problem is that 0.05B, how to take that 0.05B into account. So that you have to take separately. You have to perform a separate analysis, static analysis, where you consider that torsion and then add that as part of your earthquake analysis. So there is no direct way in which you can consider 0.05B directly in your 3D analysis.
The next question is from Mr. Sutar. What maximum ratio of horizontal to vertical dimension to be maintained for flaring a column? Again, it's a question on
flaring of the column is dangerous. It should not be done.
Okay, the question is, can we have an inclined column? What will be the implication in analysis and what are the additional parameters to be considered?
We can, but what we have to do is we have to identify the yield mechanism. So when we are having an inclined column, then it will be subjected to large axial force and bending moment both. And our structural system, we have to see that where the plastic hinges will form. So I will suggest a nonlinear analysis, and capacity design is to be done in such a way that hinges are not forming in this incline.
Okay, just a seed of thought where we have to flare those columns, which you feel is a little tricky issue. Can we provide shear walls instead of a column at the ground level, and then subsequently it gets converted into a column on the upper stories?
But there also this problem of upper column being out than outer side of the ground story will not be solved. It will only, it can only solve that the bending moment capacity of the ground story column will be enhanced.
The
So
hinge
that,
formation, yeah, right.
so if you want to design that ground column with sufficiently large dimension with R is equal to 1, then it will solve the problem.
Probably work.
Must
Yeah,
make,
right.
if you have to do in any case that there is no other choice, then you model the flared column and the bottom column with eccentricity. Whatever eccentricity is there, that you should, your model should consider. Perform an analysis, and ground column you design with R is equal to 1.
Right. Okay, so next question is the transfer girder supporting tower columns at the podium top level should add to the stiffness of already stiff backstay level. What effect it will have on the structure? So he's having a case where the main structure, the tower structure, few columns are floated at the podium level, top podium level, and transfer girders are provided at the top level.
So there is no problem. I mean, if it is adding to the stiffness of back, still let it add. What is the problem?
Yeah, you have to
But
analyze.
we have to provide. That can't be an excuse not to provide transfer. Transfer girder is to be provided. If we are having a column starting from top of podium, we have to provide a transfer.
In case of buildings with all rectangular columns, many columns will fail before beams during earthquake. Is it true? So he is probably asking whether
No, it
the
is
hinge
not true.
formation.
You can design rectangular columns, but those rectangular columns should also be ensured
Sufficiently
to have,
strong, yeah.
have capacity 1.4 times the beams in that particular direction.
One last question, if the last question from that particular participant. If center of mass of building is at one end of rectangular building, then it goes into torsion, then what to do? So
you have to check that
you have to check
should
the
not be torsionally
irregularity.
irregular. If it is torsionally irregular, you have to balance the building. So whichever side is the mass, the stiffness should also be shifted in that direction. So you have to provide larger column or larger shear wall on that side, so that the center of stiffness and center of mass both coincide.
Okay, the next question is, since majority of the tall residential buildings are constructed probably with system shuttering, now with RCC walls, like, my one system, I guess we need separate code for such buildings where redundancy is too high and entire system acts as a 3D unit.
Yes.
I think it's a good suggestion.
Before the code, we need research, because from where they will make the code if no information is available. So first we have to do research, we have to do testing, then only code can come.
Sir, do we need to consider earthquake forces in buried structures like box type bridges?
Yes. This is a misconception. People think that on buried structure there is no earthquake force. So this misconception I have seen at many places. Buried structures are also subjected to earthquake force, and not only earthquake force, those are subjected to distortion due to movement of earthquake soil layers. So these need to be designed for those.
I request Arvind to take up next few questions.
For less than 4-story building, top story shows higher steel and bending moment. What should be our approach for design of such short structure? That is because of
the PM interaction, because axial force. So whatever is the requirement, we have to provide.
That is mainly because of sometimes long span beams transferring a lot of dead load plus live load moments actually.
Yeah, that may also happen, but perhaps it is because of the columns.
Yeah.
Because in columns, bottom stories are having slightly higher axial force, so the moment capacity increases. But when we go in the top story, the axial force is very small, and due to that, the moment capacity reduces. Moment capacity from PM interaction curve of column reduces, and as a result, more reinforcement may be required at the top.
Yeah.
So whatever reinforcement we are getting, we have to provide.
We are all checking all irregularities with service model, but as per IS 1893 modifier, it should be checked with strength model. So which modifier we will take to check irregularity, strength or service model? Strength or service model? Because as per IS 1893, it should be checked with strength model.
It has to be checked with strength modifiers. Earthquake has only one type of modifiers. Earthquake is not a serviceability problem. Earthquake is always an ultimate problem.
Strength.
So,
Please suggest when to assign rigid and semi-rigid diaphragm. That will affect on geometry actually.
so criteria is given in the code.
Yeah.
You have to calculate the deformation within the slab and compare it with the interstory drift. So IS 1893 provides that criteria. Based on that criteria, you have to decide.
There is also a clause which says about the percentage of openings also.
Right.
Can we consider P delta effect in service model? Can we or shall we? What is the question? It's not clear. But P delta effect in service model.
I mean, all the software have that command. I do not know what's the difficulty. So, but we have to consider.
Yeah. I just lost.
Yeah, just last two questions now.
Yeah. It is from where the distance between center of mass and stiffness varies from floor to floor. How does one determine a single value for the entire structure?
Yeah, so on every floor, actually you don't need, code does not ask to, at least up till now, maybe the revised code will ask and then we have to check it every floor. At the moment, the code asks to determine delta max by delta min. So maximum displacement to minimum displacement. And that is to be checked at every floor. And none of the floor, it should be more than the limit.
Either that we are already answered.
Okay.
Can we model shear wall of slightly less thickness than we are designing, and after that we design actual column size in RCDC? Wall thickness is in control. I don't think such jugglery should be done. Okay.
Not clear to me.
Yeah. Correct.
Okay, I think
We should.
we have covered almost all the questions, and we should conclude here.
I think 1 second, I'll take this last. How can we model masonry basement walls of a residential building of low height in a seismic zone 5 where there is vertical irregularity because one part of the building is founded at lower level than the other?
So by masonry wall, it is meant masonry infill or the building itself is masonry?
Yeah, that's not clear. But I think
it looks like that he is talking about RCC building with masonry.
With masonry infill walls.
Okay. So
I think the question is probably like this. The building is having the base at the two different levels. Part of it is having a basement kind of a structure because of the site contours, and the upper portion is having a regular ground floor with walls, and the lower portion is having no infill walls. They are without infill walls. So probably he's trying to ask us what to do, how to deal with this situation.
So means it's sort of a sloping terrain, a hillside building with one side on a stilt.
Correct.
So in such cases, those stilts should be strong enough. So in theoretically, there should be a nonlinear analysis. We have to ensure that those columns and beams without infill should not fail. But what we have seen that if you, I mean, this experience which I was sharing, that if you design as per code, performing a 3D model, taking torsion into account and following a strong column weak beam ratio of 1.4, then hinges will not form before cracking of the shear wall at the top. I mean, these infill walls at the top.
I think that's all. We can conclude, I think. Then to finish.
Okay, so thank you.
So should we
Thank you very
propose
much.
A vote of thanks.
vote of thanks? Yeah.
Okay.
Yes. Sir, first of all, I would like to thank Dr. Yogendra Singh. With his busy schedule, we managed to have at least 2 or 3 workshop or webinars in a year. He is a very popular teacher and we don't have to make many efforts to get the participant. Only his name is enough. Also, I must thank all the participants because they have come in a good number and from various states of India. I will share that with Yogendra Singh sir. Now, few words about us that we are into structural design, proof checking of tall building, structural audit, assessment and identity, concrete quality monitoring, project management consultancy, architecture and engineering, and of course, training through EFC. So if you have any specific subject in mind, please do inform us. If any one of your questions is unanswered, write to us. We'll try to get it sorted out to Dr. Yogendra Singh and compile and send it to you. Thank you, sir.
Thank you.
Thank you. Thank
Thank
you,
you.
Prathanik, and I'm thankful to Epicons for arranging these workshops in offline as well as online mode. I wish this workshop also we were face to face because that gives a lot of energy to me also. But whatever we can manage, that's better. That's good.
And lastly,
Thank you
sir,
very much, and all the participants, thank you very much for coming this large number. I'm always afraid that I may be repeating after some time the things which I have covered earlier. It may be boring to you people, and I don't want that. So please just let me know if you feel it interesting, good. If you think that now we are repeating, we will give a break till something new comes out. And
sir, it is not like that. There are always new and new participant one. Secondly, subject is so difficult that hearing it from you or a good guru is always refreshing us. And as I told in the beginning, that from Remedios, we used to have at least one physical workshop in 6 months on site because at that time concrete technology was not advanced and he used to teach various ways of doing good concrete at site, which included mixed design as well as shuttering design as well as actual practices in pouring and compaction. So that has given us energy to have good good teacher should reach the smallest corner of the India. Thank you, sir.
He used to take
Yes.
the same contents for years.
But in this case, what we can say, or in this case, we can say that though the subject is same, we could see that the content is modified. There is a lot of R&D is done and those sites have been added. So those are quite, it's quite useful for all of us. Yeah. Thank you.
And as
Thank you.
requested to you, we would like to have a session on the new, that is draft version of 13920. They have asked comment before 3rd of August. So we're already appealing to all the participants to put forward their question, but still you can give some initiative. So we intend to do it on 20th of July so that at least 2 weeks are there for participants to think and put forward their question. Thank you, sir.
Okay.
Thank you.
Will do. Thank you.
So we are signing off. Thank you.